Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of an ancient visitor that has crossed the vast emptiness between stars to grace our small corner of the universe. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the autumn of 2019, a machine awakens in Hawaii. The asteroid terrestrial impact last alert system, Atlas, begins another night of its eternal vigil, scanning the darkness with silicon eyes that never blink, never tire, never look away. The telescope moves with mechanical precision across predetermined coordinates, each exposure capturing light that has traveled unimaginable distances to reach this moment. Within the digital grid of pixels, something appears that should not exist. A point of light moves against the stellar background with purposeful direction. Too fast for an asteroid, too bright for ordinary debris. The automated systems flag this anomaly with clinical efficiency, assigning it a designation that will echo through observatories worldwide. C2019 L3, later renamed 3I/Atlas, the third confirmed interstellar visitor to our solar system, has announced its presence with the faintest whisper of reflected sunlight. Scientists studying the discovery images notice immediately what makes this visitor extraordinary, unlike the angular, metallic fragments that typically wander between planets. 3. I/Atlas displays a subtle but unmistakable fuzzy appearance, the signature of outgassing that marks it as a comet rather than an asteroid. Water ice locked within its nucleus begins to sublimate as solar radiation touches surfaces that have known only the absolute cold of interstellar space for millions of years. The process creates a thin atmosphere of vapor and dust that catches and scatters our star's light like morning mist in a garden. The comet's brightness increases steadily as it approaches the inner solar system, following laws of physics that govern all matter regardless of its origin. Yet there remains something unsettling about this visitor's behavior, something that suggests it carries more than mere ice and rock across the cosmic void. Astronomers detect subtle variations in its light curve that hint at complex rotation patterns, as if the object tumbles through space with a memory of ancient gravitational encounters in regions beyond our sun's influence. Ground-based telescopes around the world turn their attention to this wandering fragment of another stellar system. The European Southern Observatory's Very Large Telescope Array captures spectra that reveal the chemical composition of Atlas's coma, that tenuous envelope of gas and dust that forms as the comet's nucleus heats under solar radiation. The signatures of water vapor appear first, followed by traces of carbon monoxide and other simple molecules that tell stories of formation in the frigid outer reaches of a distant planetary system. Professional observers note with quiet fascination that Atlas follows a hyperbolic orbit, meaning it will make only one passage through our solar system before returning to the galactic wilderness from which it emerged. This single encounter represents humanity's only opportunity to study materials that condense from the primordial disk surrounding a star whose light has not yet reached Earth. The visitor carries within its frozen nucleus a chemical record of conditions that existed billions of years ago in a stellar nursery that may no longer exist. Radio telescopes detect the faint emissions that accompany Atlas's outgassing, electromagnetic signatures that speak of molecular bonds breaking under the sun's influence. These signals, barely distinguishable from background cosmic noise, represent conversations between atoms that formed in the vicinity of another star. The comet becomes a temporary radio source, broadcasting on frequencies that encode information about temperature, composition, and the subtle physics of sublimation in near-vacuum conditions. Planetary defense networks monitor Atlas's trajectory with the same automated vigilance they apply to potentially hazardous asteroids. Computer models calculate the visitor's path with extraordinary precision, confirming that it will pass harmlessly through the inner solar system before beginning its journey back to interstellar space. The calculations reveal orbital parameters that suggest Atlas originated from the direction of the constellation Lynx, though its true birthplace remains lost in the statistical uncertainty that accumulates over millions of years of gravitational perturbations. Amateur astronomers contribute their own observations to the growing database of Atlas measurements. Backyard telescopes equipped with sensitive CCD cameras capture images that, when combined with professional data, help refine the comet's orbital elements and rotation period. This collaborative effort represents one of astronomy's most democratic traditions, the shared pursuit of knowledge about objects that belong to no single nation or institution, but to the entire cosmos. The visitor's nucleus, estimated to be several hundred meters in diameter, contains more water ice than all of Earth's rivers combined, yet this abundance represents only a tiny fraction of the original comet that began this journey eons ago. Solar radiation and cosmic ray bombardment have slowly eroded Atlas's surface over the millennia, leaving behind a core of the most refractory materials, silicates and organic compounds that require higher temperatures to vaporize. Spectroscopic analysis reveals the presence of complex carbon-bearing molecules within Atlas's coma, including some that may be precursors to the biochemical compounds essential for life as we know it. These organic materials survived the harsh conditions of interstellar space, protected within the comet's interior by layers of ice and dust that acted as natural shielding against destructive radiation. The visitor becomes a time capsule, preserving chemical complexity from an era when our own solar system was still condensing from its natal cloud. Infrared observations detect the thermal signature of Atlas's nucleus as it absorbs and re-radiates solar energy. The temperature measurements reveal a surface darker than charcoal, coated with a layer of dust and organic residue that accumulated during the comet's long journey between stars. This protective mantle regulates the rate of sublimation, creating a feedback mechanism that has allowed the visitor to survive its passage through the hostile environment of interstellar space. The comet's tail, invisible to the naked eye but clearly recorded by sensitive cameras, extends for millions of kilometers in the direction opposite the Sun. Solar wind, the stream of charged particles flowing outward from our star, shapes this tenuous appendage into a graceful curve that follows the magnetic field lines threading through the inner solar system. The tail becomes a temporary feature of local space, a ghostly banner that will dissipate once Atlas moves beyond the Sun's immediate influence. Navigation software aboard distant spacecraft automatically updates their star catalogs to account for Atlas's presence, treating the visitor as a temporary addition to the celestial reference frame used for interplanetary travel. The comet becomes briefly incorporated into humanity's expanding map of the solar system, a waypoint that will be remembered long after the object itself has faded beyond the reach of our most powerful telescopes. Deep space monitoring stations record the subtle gravitational effects that Atlas exerts on nearby objects, measurements that contribute to increasingly precise models of solar system dynamics. Though the comet's mass is negligible compared to the planets, its influence can be detected through careful analysis of spacecraft trajectories and the orbital perturbations of small asteroids that happen to pass within its gravitational reach. As Atlas continues its approach toward perihelion, the closest point in its solar orbit, the rate of outgassing accelerates, creating a more prominent coma and extending the comet's tail to greater lengths. The visitor begins to resemble its more familiar cousins from the outer solar system, though it will never develop the spectacular appearance of comets that originate from our Sun's own Oort cloud. Atlas remains a subtle presence, visible only through the patient accumulation of photons by instruments designed to detect the faintest traces of cosmic light. The discovery of 3I/Atlas represents more than the identification of another celestial wanderer. It offers humanity a glimpse into the processes that operate on galactic scales. The slow exchange of material between stellar systems that has continued for billions of years since the first generation of stars began enriching the cosmos with heavy elements. The visitor carries within its nucleus the chemical signature of stellar nucleosynthesis that occurred in regions of space unimaginably distant from our own. The first clue to Atlas's true nature emerges not from its appearance, but from its behavior under the sun's influence. As the visitor draws closer to our star, instruments detect a gradual brightening that follows patterns familiar to comet researchers, but distinctly different from the constant reflectivity expected of rocky asteroids. The brightening occurs in subtle pulses and variations that speak of active processes occurring within the object's nucleus, ice transforming directly from solid to gas, bypassing the liquid phase entirely in the near vacuum of space. Spectroscopic observations reveal the telltale signatures of water vapor in Atlas's expanding coma. Molecules that absorb and emit light at specific wavelengths determined by the quantum mechanics of hydrogen and oxygen bonds. These absorption lines appear as dark features in the comet's spectrum, cosmic fingerprints that confirm the presence of H2O molecules moving at velocities of several hundred meters per second as they escape the visitor's weak gravitational field. The detection represents humanity's first direct chemical analysis of water that condensed in the vicinity of another star. The European Space Agency's ground-based telescopes capture high-resolution images that show Atlas developing the characteristic fuzzy appearance of an active comet. Unlike the sharp, star-like points of light that mark asteroids in long-exposure photographs, the visitor displays a distinct halo of scattered material that extends for thousands of kilometers around its solid nucleus. This coma forms as solar radiation heats the comet's surface, causing volatile compounds to sublimate and carry away microscopic dust particles that have remained frozen in place for millions of years. Radio astronomy facilities detect emissions from hydroxyl radicals, O molecules created when solar ultraviolet light breaks apart water vapor molecules in Atlas's coma. These fragments exist for only brief moments before recombining or dissociating further. But their radio signatures provide detailed information about the physical conditions within the comet's tenuous atmosphere. The signals arrive at Earth with frequency shifts that reveal the rotational motion of the gas cloud, allowing scientists to map the three-dimensional structure of the visitor's activity. Thermal infrared measurements indicate that Atlas's nucleus has a very low albedo, reflecting less than 4% of the sunlight that strikes its surface. This dark coloration suggests a coating of organic compounds and dust that accumulated during the object's journey through interstellar space, materials that have been processed by cosmic radiation into complex carbon-bearing molecules. The surface resembles a cosmic tar ball, blackened by eons of exposure to high-energy particles that break down and recombine simple compounds into increasingly elaborate chemical structures. Photometric observations reveal that Atlas rotates with a period of approximately 7 hours, tumbling slowly as it travels through space with an axis of rotation that appears to wobble over longer timescales. This complex rotational behavior may result from the irregular shape of the nucleus combined with the subtle torques generated by outgassing. Jets of vapor escaping from active regions on the comet's surface create tiny but persistent forces that gradually alter the visitor's spin state over months and years. The comet's activity level increases steadily as it approaches the inner solar system, following well-established laws that govern the sublimation of ice under varying intensities of solar radiation. Computer models predict the visitor's brightness based on its distance from the sun, and observations confirm these theoretical expectations with remarkable precision. Atlas behaves exactly as scientists would expect for a comet nucleus, composed primarily of water ice mixed with dust and rocky debris. Ground-based observatories detect periodic variations in Atlas's brightness that correspond to its 7-hour rotation period, indicating that the nucleus has an irregular shape with distinct regions of varying reflectivity. Some areas of the surface appear more active than others, producing stronger jets of gas and dust that create temporary brightness enhancements visible from Earth. These active regions may represent areas where the protective dust mantle has been blown away, exposing fresh ice deposits to direct solar heating. High-resolution spectroscopy reveals additional molecular species within Atlas's coma, including carbon monoxide, carbon dioxide, and various hydrocarbon compounds that provide clues about the chemical conditions present during the comet's formation. The relative abundances of these molecules suggest that Atlas formed in a cold outer region of its parent stellar system, where temperatures remained low enough to condense even the most volatile compounds into solid ice. Astrometric measurements track Atlas's position with extraordinary precision, allowing astronomers to refine their calculations of the visitor's orbital elements and predict its future trajectory through the solar system. The observations reveal subtle non-gravitational accelerations caused by the rocket effect of outgassing, as material sublimes from the nucleus and escapes into space. It imparts a tiny but measurable thrust that gradually alters the comet's orbit in ways that pure gravitational mechanics cannot explain. Amateur astronomers around the world contribute their own observations to the growing database of Atlas measurements, using backyard telescopes equipped with digital cameras to monitor the comet's brightness and activity level. These citizen scientists provide valuable long-term coverage that complements the more intensive but shorter duration observations conducted by professional observatories, creating a comprehensive record of the visitor's behavior as it traverses our solar system. The discovery that Atlas is a comet rather than an asteroid carries profound implications for our understanding of interstellar space and the processes that allow fragile, ice-rich objects to survive journeys lasting millions of years. Theoretical models suggest that such visitors must originate from the outer regions of distant planetary systems, where gravitational perturbations can occasionally eject comets from their stable orbits and send them wandering through the galaxy. Atlas represents direct observational evidence that these long-range exchange processes actually occur. Comparative studies with the previous interstellar visitors, Oumuamua and 2I/Borisov, reveal both similarities and striking differences in composition and behavior. While 2I/Borisov displayed obvious cometary characteristics from the moment of its discovery, and Oumuamua showed puzzling non-gravitational accelerations that may have resulted from hydrogen outgassing. Atlas follows a more conventional pattern of comet activity that aligns closely with theoretical predictions for interstellar objects. The visitor's chemical composition provides insights into the formation processes that operated in its parent stellar system billions of years ago. The isotopic ratios of hydrogen, carbon, and oxygen within Atlas's water and carbon-bearing compounds may differ subtly from those found in solar system comets, potentially revealing variations in the primordial materials from which different stellar systems condensed. These measurements require the most sensitive analytical techniques available to modern astronomy, pushing the limits of spectroscopic precision. Polarimetric observations analyze the way light waves oscillate after reflecting from dust particles in Atlas's coma, providing information about the size, shape, and composition of the microscopic grains being expelled from the nucleus. The polarization properties suggest that the dust consists primarily of silicate minerals similar to those found in solar system comets, indicating that the basic processes of planetary formation operate similarly around different types of stars. The comet's tail, though much fainter than those of spectacular naked-eye comets, extends for several million kilometers in the anti-solar direction and shows the characteristic dual structure of ion and dust components. The ion tail, composed of electrically charged molecules, follows the magnetic field lines embedded in the solar wind and appears blue-green in color due to emissions from carbon monoxide and other ionized species. The dust tail, formed by larger particles that respond primarily to radiation pressure, curves more gently and reflects sunlight with a neutral yellowish hue. Long-term monitoring reveals that Atlas's activity level varies not only with solar distance, but also with the visitor's rotational phase, confirming that outgassing occurs preferentially from specific regions on the nucleus surface. These active areas may represent locations where impacts or thermal cycling have fractured the protective dust mantle, creating pathways for subsurface ice to reach areas where it can sublimate under solar heating. The pattern of activity provides an indirect map of the comet's surface geology. The mathematics of Atlas's journey through space tell a story that stretches across geological epochs. Orbital calculations trace the visitor's path backward through time, following gravitational breadcrumbs that lead far beyond the outer boundaries of our solar system. Computer models reconstruct the comet's trajectory over the past several million years, accounting for the subtle influences of every planet, every major asteroid, and the galactic tide itself, that gentle but persistent force exerted by the Milky Way's rotation on objects at the very edge of the Sun's gravitational domain. The backwards extrapolation reveals that Atlas entered our solar system from the general direction of the constellation Lynx, arriving with a velocity of approximately 26 kilometers per second relative to the Sun. This speed exceeds the escape velocity of our stellar system, confirming beyond doubt that the visitor originated elsewhere in the galaxy. The excess velocity speaks of eons spent traveling through the interstellar medium, that tenuous soup of gas and dust that fills the space between stars with densities so low that the best laboratory vacuums on Earth appear dense by comparison. During its million-year journey through the void, Atlas experienced conditions utterly foreign to objects that remain gravitationally bound to stellar systems. The temperature of its surface approached absolute zero, warmed only by the faint glow of background radiation left over from the universe's formation and the occasional cosmic ray impact. In this frigid environment, even helium would freeze solid, and the comet's nucleus became a block of ice harder than granite, its volatile compounds locked in crystalline matrices that preserve the chemical conditions present at the moment of its ejection from its parent system. The interstellar medium through which Atlas traveled consists primarily of hydrogen atoms and molecules, with trace amounts of heavier elements synthesized in the cores of ancient stars and dispersed by stellar winds and supernova explosions. This material exists at densities averaging 1 atom per cubic centimeter, a vacuum so perfect that it would take millions of years for enough atoms to accumulate on the comet's surface to form a layer 1 molecule thick. Yet even this minimal interaction left subtle traces on Atlas's chemistry, as high-energy cosmic rays occasionally struck the nucleus and created new isotopes through nuclear transmutation. Gravitational perturbations from passing stars altered Atlas's trajectory countless times during its interstellar voyage. The galaxy contains over 100 billion stars, and statistical calculations suggest that the comet passed within a few light-years of dozens of stellar systems during its journey. Each encounter modified the visitor's path slightly, creating a complex orbital history that can never be fully reconstructed despite the precision of modern computational techniques. The comet's current trajectory represents the cumulative result of millions of these minute gravitational nudges. The Oort cloud comets native to our solar system provide a reference point for understanding Atlas's probable origin. These objects orbit at distances of tens of thousands of astronomical units from the Sun, where they remain frozen for billions of years until gravitational perturbations send them falling inward toward the inner planets. Atlas likely began its journey from a similar reservoir surrounding another star, ejected by gravitational interactions with passing objects or the tidal forces generated by close stellar encounters. Models of galactic dynamics suggest that interstellar objects like Atlas represent a vast population of wandering bodies that populate the spaces between stars. Every planetary system likely contributes to this galactic reservoir through ejection events that occur throughout stellar evolution. Young stars surrounded by massive protoplanetary disks may expel large numbers of small bodies through gravitational interactions, while mature systems continue to lose objects through the gradual erosion of their outer comet clouds. The galaxy becomes a vast exchange network, continuously trading small bodies between stellar systems. The visitor's chemical composition provides clues about the environment in which it formed billions of years ago. The isotopic ratios locked within Atlas's ice record the nuclear processes that occurred in its parent star's fusion core, along with contributions from nearby supernovae that enrich the local interstellar medium with heavy elements. These signatures remain preserved within the comet's frozen nucleus like pages in an ancient book, waiting to be read by spectroscopic techniques that can analyze individual molecular species within the expanding coma. Cosmic ray bombardment during Atlas's journey through space gradually modified the surface composition of the nucleus, breaking down complex organic molecules and creating new chemical compounds through radiolysis. High-energy particles penetrated several meters into the comet's interior, leaving a trail of damaged crystal structures and altered chemistry that accumulated over millions of years of exposure. The surface layer of the nucleus became darkened and enriched in carbon-bearing residues that formed when radiation broke apart more complex molecules. The magnetic field embedded in the solar wind provides another tool for studying Atlas's journey through space. As the comet's ionized coma interacts with these magnetic field lines, it creates detectable disturbances that can be measured by spacecraft throughout the inner solar system. These magnetic signatures provide information about the density and composition of the visitor's gas cloud, while also revealing details about the solar wind conditions in the comet's immediate vicinity. During its approach through the outer solar system, Atlas passed through regions where the solar wind begins to weaken and interact with the surrounding interstellar medium. This boundary region, known as the heliosheath, represents the edge of our Sun's direct influence and marks the transition between truly interstellar space and the solar environment. The comet carried with it chemical and isotopic signatures from beyond this boundary, providing a unique opportunity to study materials that formed under conditions never directly sampled by human-made instruments. The mechanics of Atlas's capture into a bound solar orbit would have required an extraordinarily precise set of circumstances. The comet's initial velocity upon entering the solar system was too high for permanent gravitational capture by the Sun alone. Only a close encounter with one of the outer planets could have reduced its velocity sufficiently to create a bound orbit, and the probability of such an encounter occurring at exactly the right time and distance approaches astronomical improbability. Instead, Atlas follows a hyperbolic trajectory that will carry it back to interstellar space after its single passage through the inner planets. The visitor's rotation state carries information about its dynamical history and the processes that shaped its nucleus over millions of years. The current 7-hour rotation period may result from countless small collisions with interstellar dust grains, each impact imparting a tiny torque that gradually spun up the nucleus over geological timescales. Alternatively, the rotation may have been established during the comet's original ejection from its parent system, when gravitational torques from nearby planets could have imparted significant angular momentum to the departing object. Statistical studies of known interstellar objects suggest that visitors like Atlas arrive in our solar system approximately once per year, though most remain too faint to detect with current astronomical survey programs. Improved telescope technology and more sensitive detection algorithms will likely reveal a steady stream of these cosmic wanderers, each carrying unique information about conditions in distant stellar systems. Atlas represents not an anomaly, but a member of a vast population of objects that connect every star in the galaxy through slow exchanges of material that operate over timescales longer than the age of complex life on Earth. The discovery of multiple interstellar visitors within the span of a few years suggests that the space around our solar system contains a significant population of such objects at any given time. Most remain invisible, too small and distant to reflect enough sunlight for detection by ground-based telescopes. Atlas likely shares the outer solar system with dozens or hundreds of similar visitors, each following its own trajectory through the gravitational landscape defined by our star and its family of planets. Theoretical models predict that the number of interstellar objects in the vicinity of our solar system should vary with our location within the galaxy's spiral structure. As the solar system orbits the galactic center, it passes through regions of different stellar density and encounters varying populations of ejected objects from nearby stars. The current era may represent a period of relatively high interstellar traffic, as our Sun travels through one of the galaxy's spiral arms, where stellar densities and interaction rates remain elevated compared to the quieter regions between spiral features. The light that carries information about Atlas across the vast emptiness of space arrives at Earth as individual photons, each one encoding specific details about the molecules present in the comet's expanding coma. These particles of electromagnetic radiation began their journey at the comet's nucleus, where solar photons first struck the dark surface and were either absorbed or reflected back into space. The reflected light carries within its spectrum the fingerprints of atoms and molecules that absorbed or scattered the radiation at characteristic wavelengths determined by the quantum mechanical properties of matter itself. Spectroscopy transforms this encoded light into readable chemical information through instruments that separate the incoming radiation into its component colors with the same precision that a prism disperses white light into rainbows. High-resolution spectrographs attached to major telescopes around the world capture Atlas's spectrum across wavelengths ranging from deep ultraviolet to thermal infrared, revealing absorption and emission lines that correspond to specific electronic transitions within atoms and vibrational modes within molecules. Each spectral feature represents a unique signature that allows scientists to identify chemical compounds with the same certainty that fingerprints identify individual humans. The most prominent features in Atlas's spectrum belong to water vapor, appearing as a series of absorption lines in the near-infrared region where H2O molecules transition between different rotational and vibrational energy states. These lines reveal not only the presence of water, but also its temperature, density, and velocity within the comet's coma. The width of each spectral line indicates the range of molecular velocities present in the gas cloud, while the intensity reveals the total number of water molecules along the line of sight between Earth and the comet's nucleus. Hydroxyl radicals created by the photodissociation of water molecules produce their own distinctive spectral signatures, appearing as emission lines in the ultraviolet and radio portions of the electromagnetic spectrum. The OH radical exists only briefly before recombining with other molecules or dissociating completely, but during its short lifetime it acts as a powerful beacon that reveals the rate at which solar radiation breaks apart water vapor in the comet's vicinity. Radio telescopes detect the 18-centimeter emission line of hydroxyl with extraordinary sensitivity, allowing astronomers to map the three-dimensional structure of Atlas's gas cloud with resolution measured in thousands of kilometers. Carbon-bearing molecules within the coma produce additional spectral features that provide insights into the organic chemistry present in Atlas's nucleus. Carbon monoxide appears as a series of rotational lines in the millimeter wave portion of the spectrum, while carbon dioxide creates absorption features in the infrared. More complex organic compounds contribute weaker signals that require the most sensitive instruments to detect, but their presence confirms that Atlas carries the same types of carbon-based molecules that form the foundation of biochemistry on Earth. The isotopic composition of Atlas's molecules can be determined through careful analysis of subtle shifts in spectral line positions caused by the different masses of atomic isotopes. Heavy water, containing deuterium instead of ordinary hydrogen, produces absorption lines that are shifted slightly from those of normal H2O. The ratio of deuterium to hydrogen within the comet's water provides crucial information about the temperature and radiation environment present during the formation of Atlas's parent stellar system billions of years ago. Polarimetry adds another dimension to the analysis of Atlas's light by measuring the orientation of electromagnetic wave oscillations after they interact with dust particles in the comet's coma. The degree and angle of polarization depend on the size, shape, and composition of the microscopic grains that scatter the sunlight, providing information that cannot be obtained through spectroscopy alone. These measurements reveal that Atlas's dust consists primarily of silicate minerals similar to those found in meteorites, with grain sizes ranging from nanometers to micrometers. The thermal emission from Atlas's nucleus provides direct measurements of surface temperature and thermal inertia, properties that reveal details about the physical structure and composition of the solid nucleus beneath its tenuous atmosphere. Infrared observations detect the heat radiated by the comet's surface as it absorbs solar energy during the day and slowly cools during the night. The temperature variations follow predictable patterns based on the nucleus's rotation period and the thermal properties of the surface materials. Photometric measurements track changes in Atlas's brightness over time, revealing both the overall increase in activity as the comet approaches the Sun and periodic variations caused by the nucleus's rotation. Light curves constructed from thousands of individual brightness measurements show that different regions of the comet's surface have varying levels of activity, with some areas producing stronger outgassing than others. These brightness variations provide indirect maps of the nucleus's surface geology and composition. Radio observations at multiple frequencies probe different depths within Atlas's coma, from the dense inner regions where molecules first escape the nucleus to the outer boundaries where the solar wind begins to dominate the local environment. Low-frequency radio waves interact with the ionized component of the coma, revealing the presence of electrically charged molecules and providing information about plasma physics processes that operate in the rarefied environment surrounding the comet's nucleus. The Doppler effect shifts the wavelengths of spectral lines based on the relative velocity between Atlas and Earth, allowing astronomers to measure the comet's approach velocity with extraordinary precision. Additional Doppler shifts caused by the expansion of the coma reveal the velocities at which gas molecules escape from the nucleus, providing information about the temperature and gravitational field strength at the comet's surface. These measurements confirm that Atlas has a very weak gravitational field, unable to retain gas molecules moving faster than a few hundred meters per second. High-resolution imaging in different wavelengths reveals the spatial distribution of various molecular species within Atlas's coma, showing how water vapor, hydroxyl radicals, and other compounds are distributed around the nucleus. The images reveal jet-like structures where active regions on the comet's surface expel material into space, creating temporary enhancements in gas density that can be tracked as they expand and fade over periods of hours or days. The analysis of forbidden emission lines, spectral features that occur only under the extremely low-density conditions present in space, provides unique insights into the physical environment within Atlas's coma. These transitions, which cannot occur in terrestrial laboratories due to collisional de-excitation, reveal information about electron densities, magnetic field strengths, and the degree of ionization present in the comet's tenuous atmosphere. The detection of these lines confirms that Atlas's coma represents one of the most perfect vacuums in the solar system. Comparison of Atlas's spectrum with those of solar system comets reveals both similarities and subtle differences that may reflect the distinct formation environments of objects that originated around different stars. While the basic molecular inventory remains similar, water, carbon monoxide, carbon dioxide, and simple organic compounds, the relative abundances and isotopic ratios may carry signatures of the nuclear processes that operated in Atlas's parent star and the chemical conditions present in its birth stellar system. The temporal evolution of Atlas's spectrum tracks the changing activity level as the comet responds to varying intensities of solar radiation during its passage through the inner solar system. Spectral lines become stronger and broader as outgassing rates increase, while new molecular species appear as different types of ice begin to sublimate at higher temperatures. The progression provides a detailed record of how the comet's nucleus responds to solar heating, revealing the layered structure of different volatile compounds beneath the protective dust mantle. Laboratory experiments using samples of terrestrial ice mixed with dust and organic compounds help calibrate the interpretation of Atlas's spectral features. These analog studies reveal how different molecular species behave under the extreme conditions present in space, where temperatures remain hundreds of degrees below freezing and pressures approach the perfect vacuum of interstellar space. The experiments confirm that the spectroscopic signatures observed from Atlas are consistent with a nucleus composed primarily of water ice contaminated with dust and organic materials. Machine learning algorithms trained on databases of known spectral features can automatically identify molecular species within Atlas's complex spectrum, detecting weak signals that might be overlooked by human analysts. These computational techniques become increasingly important as instruments achieve higher spectral resolution and sensitivity, generating datasets that contain millions of individual wavelength measurements. The algorithms can identify trace constituents that comprise less than 1% of the total molecular inventory, but still produce detectable spectral signatures. The study of Atlas's chemical composition through spectroscopy represents one of humanity's most ambitious analytical challenges, determining the detailed molecular inventory of an object located millions of kilometers away using only the information carried by particles of light that have traveled across the solar system. The success of these measurements demonstrates the extraordinary power of modern astronomical techniques to decode the secrets hidden within electromagnetic radiation, transforming photons into knowledge about the fundamental processes that operate throughout the universe. The gravitational architecture of our solar system reveals itself through Atlas's trajectory with mathematical precision that would satisfy Newton himself. As the interstellar visitor approaches the Sun, its path bends according to the inverse square law that governs all gravitational interactions, following a hyperbolic curve that can be calculated to extraordinary accuracy using equations first derived 3 centuries ago. The comet's motion demonstrates the fundamental principle that gravity operates identically whether the object in question formed around our star or condensed from materials ejected by stellar systems thousands of light-years distant. Orbital mechanics describes Atlas's journey through a language of mathematical parameters that encode every aspect of its motion through space. The semi-major axis of the hyperbolic orbit measures -2.4 astronomical units, confirming that the visitor carries more than enough velocity to escape our solar system permanently. The eccentricity exceeds unity by a significant margin, quantifying the degree to which the trajectory deviates from the closed elliptical orbits that characterize gravitationally bound objects like planets and asteroids. The comet's orbital inclination of approximately 45 degrees relative to the ecliptic plane reflects its extrasolar origin, as objects native to our solar system typically orbit closer to the plane defined by planetary motions. This tilted trajectory carries Atlas above and below the disk-like region where most solar system activity occurs, providing a perspective on our stellar neighborhood that differs fundamentally from the viewpoint available to Earth-bound observers who see the cosmos from within the ecliptic plane. Perihelion, the point of closest approach to the Sun, occurs at a distance of approximately 0.3 astronomical units, placing Atlas well inside the orbit of Mercury during its brief passage through the inner solar system. At this distance, solar radiation intensity increases by a factor of more than 10,000 compared to the frigid conditions the comet experienced during its journey through interstellar space. The dramatic change in heating drives the accelerated outgassing that creates Atlas's visible coma and tail. The argument of perihelion and longitude of ascending node define the three-dimensional orientation of Atlas's orbit within the solar system's coordinate framework. These angular parameters, measured with respect to the spring equinox and the ecliptic plane, allow astronomers to predict exactly where the comet will appear in Earth's sky at any given time during its passage. The calculations account for the gravitational influences of all major planets, creating ephemeris tables accurate to within fractions of an arcsecond over periods of months or years. Computer simulations integrate Atlas's motion through the complex gravitational field created by the Sun and its retinue of planets, accounting for perturbations that modify the visitor's trajectory in subtle but measurable ways. Jupiter's massive gravitational field produces the largest perturbations, altering the comet's velocity by several meters per second and shifting its ultimate departure trajectory by a measurable angle. These gravitational interactions represent the solar system's final gift to the departing visitor, a slight modification of its orbital energy that will influence its path through the galaxy for millions of years to come. The restricted three-body problem, a classical challenge in celestial mechanics, finds practical application in analyzing Atlas's motion through regions where the gravitational influences of the Sun and Jupiter become comparable, near the Lagrange points where these competing forces balance. The comet's trajectory becomes exquisitely sensitive to small perturbations, amplifying the effects of solar radiation pressure and outgassing forces that would be negligible in other regions of space. Non-gravitational accelerations caused by the rocket effect of outgassing material create additional complexities that must be incorporated into accurate orbital predictions. As molecules sublimate from Atlas's nucleus and escape into space, they carry momentum that was originally part of the comet's orbital motion. The resulting thrust typically acts in the direction away from the Sun, but the exact magnitude and direction depend on the distribution of active regions across the nucleus surface and the comet's rotation state. The orbital energy of Atlas exceeds zero by a comfortable margin, confirming that the visitor will escape the solar system with a final velocity of approximately 20 kilometers per second relative to the Sun. This excess energy represents the kinetic energy that Atlas possessed upon entering our stellar system, minus the small amount lost to gravitational interactions with the planets and the even smaller quantity consumed by outgassing processes that reduce the comet's mass. Barycentric coordinates transform the description of Atlas's motion from the Sun-centered reference frame commonly used for planetary studies to the center of mass frame of the entire solar system. This transformation accounts for the Sun's own orbital motion around the gravitational center defined by the combined mass of all solar system objects, a point that lies slightly outside the Sun's surface due to Jupiter's significant gravitational influence. The barycentric description provides the most accurate framework for comparing Atlas's motion with that of other interstellar objects. The comet's angular momentum vector remains approximately constant throughout its passage, a consequence of the conservation laws that govern motion in central force fields. This conserved quantity determines the orientation of the orbital plane and ensures that Atlas's trajectory sweeps out equal areas in equal times, following Kepler's second law with the same precision exhibited by planets, asteroids, and comets native to our solar system. Tidal forces generated by the Sun's gravity create differential accelerations across Atlas's extended nucleus, with the sunward side experiencing slightly stronger gravitational attraction than the regions facing away from our star. These tidal stresses remain far too weak to disrupt the comet's structure, but they contribute to the complex rotational dynamics that govern the nucleus's tumbling motion through space. The periodic flexing of the nucleus may enhance outgassing from fractures and fissures that open and close in response to the changing stress patterns. The Hill sphere, the region around Atlas where its own gravity dominates over external tidal forces, extends only a few hundred meters from the nucleus surface. Within this tiny domain, the comet can temporarily capture dust particles and small debris ejected during outgassing events, creating a transient atmosphere that expands and contracts in response to the varying intensity of solar heating. Beyond the Hill sphere boundary, the Sun's gravity takes control, carrying away all expelled material and preventing Atlas from developing a substantial atmosphere. Orbital resonances with the planets create narrow zones where small perturbations can produce large changes in trajectory over extended periods. Atlas passes through several of these resonant regions during its journey, though its high velocity and hyperbolic orbit prevent it from becoming temporarily captured in the complex dynamical structures that can trap objects with lower orbital energies. The mathematical theory of resonances reveals how seemingly minor gravitational interactions can accumulate over time to produce dramatic changes in orbital evolution. The two-body approximation provides the foundation for understanding Atlas's motion, treating the comet and Sun as an isolated system unperturbed by external influences. This simplified model captures the essential physics of the orbital motion and serves as the starting point for more sophisticated calculations that include planetary perturbations, relativistic effects, and non-gravitational forces. The remarkable accuracy of the two-body solution demonstrates the dominant role of solar gravity in shaping the visitor's trajectory. Escape velocity calculations confirm that Atlas possesses more than sufficient energy to depart the solar system permanently, with no possibility of gravitational capture into a bound orbit around the Sun. The comet's velocity at infinity, the speed it will retain after climbing out of the Sun's gravitational well, exceeds the circular velocity required for a stable orbit at any distance from our star. This excess energy ensures that Atlas will rejoin the population of interstellar objects that populate the spaces between stellar systems. The orbital plane of Atlas intersects the ecliptic at 2 points called nodes, where the comet's trajectory crosses the plane containing Earth's orbit. The timing of these crossings determines whether Earth-based observers can study the visitor using telescopes located in space, or must rely on ground-based instruments that peer through the atmosphere's filtering effects. The geometry of the encounter influences which observational techniques prove most effective for analyzing the comet's composition and physical properties. Perturbation theory allows astronomers to calculate how Atlas's orbit would change if it encountered additional gravitational influences during its journey through the outer solar system. These theoretical studies reveal the sensitivity of interstellar trajectories to small changes in initial conditions, demonstrating how the chaotic nature of gravitational dynamics amplifies minor uncertainties into significant variations in long-term orbital evolution. The calculations emphasize how fortunate astronomers are to observe Atlas during its single passage through the inner planets. The orbital mechanics of Atlas's journey exemplify the universal nature of gravitational physics, demonstrating that the same mathematical principles govern motion throughout the cosmos regardless of the specific stellar system in question. The visitor's trajectory serves as a natural experiment in celestial mechanics, confirming theoretical predictions about how interstellar objects should behave when they encounter the gravitational environment of an alien star. Across the surface of Earth, a network of robotic sentinels awakens to track the progress of humanity's latest cosmic visitor. The Catalina Sky Survey's telescopes in Arizona begin their nightly dance, sweeping predetermined patches of sky with mechanical precision that never wavers, never tires, never allows personal preference to influence the systematic accumulation of data. These automated systems represent the culmination of decades of technological development, transforming the ancient art of astronomy into a precise science of digital detection and measurement. The Large Synoptic Survey Telescope, perched high in the Chilean Andes, captures Atlas within its unprecedented field of view that encompasses an area of sky equivalent to 40 full moons. Each exposure records the positions and brightnesses of millions of stellar objects simultaneously, creating a digital census of the southern sky that updates continuously throughout the night. Sophisticated software algorithms automatically identify moving objects by comparing successive images, flagging anything that has shifted position against the background of distant stars. Professional observatories around the globe coordinate their observations through international networks that ensure continuous coverage as Earth's rotation carries individual telescopes into daylight. The European Southern Observatory's Very Large Telescope Array in Chile hands off observations to the Keck telescopes in Hawaii, which in turn transfer monitoring duties to facilities in Australia and Japan. This planetary relay system allows astronomers to maintain uninterrupted surveillance of Atlas as it moves through its trajectory toward perihelion. Space-based telescopes provide unique advantages for studying the visitor, operating above the atmospheric turbulence that limits the resolution of ground-based instruments. The Hubble Space Telescope turns its aged but still precise optics toward Atlas, capturing images with clarity that reveals structural details within the comet's coma invisible from Earth's surface. The infrared capabilities of the Spitzer Space Telescope and the James Webb Space Telescope penetrate the dust shrouding the nucleus, measuring thermal emissions that encode information about surface temperature and composition. Radar systems originally designed for planetary defense applications probe Atlas with powerful microwave beams, though the comet's modest size and considerable distance place it at the extreme limit of detection capability. The Arecibo Radio Telescope, before its collapse, contributed observations that helped refine measurements of the nucleus size and rotation period. These radar studies provide direct distance measurements with accuracy measured in meters, serving as crucial calibration points for optical observations that determine position through angular measurements alone. Amateur astronomers worldwide contribute their own observations through coordinated networks that aggregate data from hundreds of small telescopes operated by dedicated volunteers. These citizen scientists provide valuable long-term monitoring that complements the more intensive but shorter duration campaigns conducted by professional observatories. Their observations help fill gaps in coverage caused by weather, equipment maintenance, or competing demands for telescope time at major facilities. The Minor Planet Center serves as the global clearinghouse for observations of Atlas, collecting measurements from observatories worldwide and combining them into increasingly precise orbital solutions. Each new observation slightly refines the calculated trajectory, reducing uncertainties in predicted positions and improving the accuracy of future ephemerides. The center's databases contain thousands of individual measurements spanning the entire duration of Atlas's visibility, creating a comprehensive record of the comet's motion through our solar system. Photometric surveys measure Atlas's brightness in multiple wavelengths simultaneously, creating detailed color measurements that reveal information about surface composition and dust properties. These multi-band observations distinguish between light reflected directly from the nucleus and emissions from gas molecules in the expanding coma, allowing astronomers to separate the contributions of solid particles and gaseous species to the comet's overall brightness. Time domain astronomy, the systematic study of how celestial objects change with time, finds perfect application in monitoring Atlas's evolving activity level as it responds to changing solar heating. Automated pipelines process new observations within hours of their acquisition, generating updated light curves that track brightness variations with temporal resolution measured in minutes. These rapid cadence measurements reveal short-term fluctuations caused by the nucleus's rotation and longer-term trends driven by increasing outgassing rates. Astrometric measurements determine Atlas's position in the sky with precision approaching 1,000th of an arcsecond. Accuracy that allows astronomers to detect subtle deviations from purely gravitational motion caused by outgassing forces. These tiny positional shifts, accumulated over months of observations, reveal the magnitude and direction of non-gravitational accelerations that modify the comet's trajectory in ways that cannot be explained by solar and planetary gravity alone. Spectroscopic surveys analyze the chemical composition of Atlas's coma through systematic observations across the electromagnetic spectrum. Radio telescopes detect emissions from hydroxyl radicals and other molecules, while optical spectrographs record absorption features created by dust particles and sublimating ice. Infrared instruments measure thermal radiation from the nucleus and identify spectral signatures of various molecular species within the tenuous atmosphere surrounding the solid core. The Deep Space Network, NASA's global array of massive radio dishes designed for spacecraft communication, occasionally turns its attention to Atlas when scheduling permits. These enormous antennas, with diameters exceeding 70 meters, can detect extremely weak radio emissions from the comet's coma and measure Doppler shifts with extraordinary precision. The network's capabilities far exceed those of conventional radio telescopes, though competition for observing time limits the frequency of such observations. Coordinated observation campaigns organize simultaneous measurements by multiple telescopes to capture rapid changes in Atlas's activity that might be missed by less frequent monitoring. These intensive studies focus on periods when the comet approaches perihelion or when unusual brightness variations suggest temporary enhancements in outgassing rates. The campaigns generate datasets with temporal and spectral resolution that would be impossible to achieve through individual observatory efforts. Machine learning algorithms process the enormous volumes of data generated by modern survey telescopes, automatically identifying interesting features and anomalies that merit follow-up observation. These computational tools can detect subtle patterns in brightness variations, unusual spectral features, or unexpected changes in orbital motion that might escape notice during manual analysis of the millions of measurements accumulated during Atlas's passage through the inner solar system. Orbital prediction software continuously updates forecasts of Atlas's future position based on the latest observational data, generating ephemerides that guide telescope pointing and observation planning. These predictions account for gravitational perturbations from all major planets, the effects of general relativity, and estimated non-gravitational forces caused by outgassing. The software provides position uncertainties that help observers determine the search area required to locate the comet in their telescope fields of view. International cooperation ensures that Atlas observations follow standardized protocols that allow measurements from different telescopes to be combined meaningfully. Common calibration standards, coordinate systems, and data formats enable seamless integration of results from observatories operated by different countries and institutions. This collaborative approach maximizes the scientific return from the global investment in astronomical infrastructure, while ensuring that no single equipment failure or adverse weather condition can interrupt the continuous monitoring of the visitor. The astronomical community's response to Atlas demonstrates the maturity of modern observational astronomy, where decades of technological development and international cooperation combine to track and study objects that would have remained completely invisible to earlier generations of astronomers. The systematic, automated nature of contemporary surveys ensures that future interstellar visitors will be detected and characterized with even greater precision. Building a comprehensive database of these cosmic messengers that connect our solar system to the broader galactic community. Real-time data sharing allows astronomers around the world to access new observations within hours of their acquisition, enabling rapid response observations when Atlas displays unexpected behavior or when atmospheric conditions at one location prevent observations that can be continued elsewhere. This global network transforms astronomy from a localized activity dependent on local weather and equipment into a planetary enterprise capable of maintaining continuous surveillance of interesting objects regardless of terrestrial complications. The technological infrastructure supporting ATLAS observations represents one of humanity's most sophisticated attempts to monitor and understand our cosmic environment. The coordinated operation of dozens of major telescopes, supported by automated data processing systems and international communication networks, creates a planetary nervous system sensitive enough to detect and track objects smaller than city blocks at distances of hundreds of millions of kilometers. This remarkable capability ensures that visitors like ATLAS receive the detailed study they deserve as representatives of the vast population of objects that populate the spaces between stars. The chemistry preserved within ATLAS's nucleus reads like a frozen library, documenting conditions that existed billions of years ago in a stellar system whose location and fate remain unknown to terrestrial observers. Spectroscopic analysis reveals an inventory of molecules that spans the periodic table, from the simplest hydrogen compounds to complex organic structures containing dozens of atoms arranged in configurations that require specific temperature and pressure conditions to form and survive. Water ice comprises the dominant constituent of ATLAS's composition, existing not as the familiar liquid that fills Earth's oceans, but as crystalline structures that formed at temperatures approaching absolute zero. These ice crystals incorporate trace amounts of dissolved gases and microscopic dust particles, creating composite materials with properties that differ significantly from pure laboratory ice. The crystalline matrix preserves the isotopic ratios of hydrogen and oxygen that were present in the molecular cloud from which ATLAS's parent stellar system condensed. Carbon monoxide frozen within the nucleus represents one of the most volatile components detected in ATLAS's spectrum, requiring temperatures below -205 degrees Celsius to remain stable in solid form. This molecule forms readily in the cold environment surrounding young stars, where carbon and oxygen atoms combine in regions shielded from the intense ultraviolet radiation that would otherwise dissociate such compounds. The preservation of carbon monoxide within ATLAS's interior suggests that the comet's nucleus has remained cold enough to prevent sublimation throughout its million-year journey through interstellar space. Methane ice appears as a minor but significant component of ATLAS's composition, detected through infrared absorption features that become more prominent as solar heating drives sublimation from the nucleus surface. This simplest hydrocarbon forms through reactions between carbon and hydrogen under the reducing conditions present in stellar nebulae, where free oxygen remains locked in water ice and metal oxides. The methane preserved in ATLAS may represent some of the most pristine organic matter in the solar system, unchanged since its formation in the vicinity of another star. Complex organic molecules create weaker but unmistakable spectral signatures that reveal the presence of carbon-bearing compounds with molecular weights reaching into the hundreds. These materials likely formed through radiation processing of simpler precursors during ATLAS's journey through space, as cosmic rays gradually built up more elaborate molecular structures through a process analogous to atmospheric chemistry, but operating over timescales measured in millions of years rather than minutes or hours. Silicate dust grains embedded throughout the ice matrix provide the rocky skeleton that gives ATLAS's nucleus its structural integrity. These microscopic particles consist primarily of magnesium and iron silicates similar to those found in terrestrial rocks, though with isotopic compositions that may differ subtly from solar system materials. The dust grains likely condensed from the hot gas surrounding ATLAS's parent star during the earliest phases of planetary system formation. When temperatures remained high enough to vaporize rock-forming elements, sulfur-bearing compounds contribute additional complexity to ATLAS's chemical inventory, appearing as hydrogen sulfide and more complex molecules that form through reactions between sulfur atoms and the abundant hydrogen and carbon present in stellar nebulae. These sulfur compounds often produce distinctive and sometimes unpleasant odors when they sublimate, though in the vacuum of space they remain purely spectroscopic phenomena detected only through their interaction with electromagnetic radiation. The nitrogen content of Atlas's nucleus remains more difficult to determine due to the relative inertness of nitrogen-bearing compounds at the temperatures present in the comet's coma. Molecular nitrogen itself produces no easily detectable spectral features under typical cometary conditions, while more reactive nitrogen compounds like ammonia may be present in quantities too small for current instruments to measure reliably. The nitrogen inventory represents one of the important unknowns in understanding the complete chemical composition of interstellar objects. Metal atoms appear in trace quantities throughout Atlas's composition, incorporated into dust grains and occasionally forming simple compounds with the more abundant light elements. Iron, magnesium, calcium, and aluminum create weak emission lines when they are released through sputtering processes that occur when high-energy solar wind particles strike the nucleus surface. These metallic components provide clues about the nucleosynthesis processes that operated in Atlas's parent star and the efficiency with which heavy elements were incorporated into solid materials during planetary system formation. The deuterium-to-hydrogen ratio within Atlas's water ice encodes information about the temperature conditions present during the comet's formation, as this isotopic ratio depends sensitively on the chemical equilibrium between gas and solid phases in cold environments. Measurements of this ratio through high-resolution spectroscopy provide one of the few direct probes of physical conditions in the outer regions of distant stellar systems where objects like Atlas are thought to originate. Noble gases trapped within the ice matrix preserve samples of the stellar wind and interstellar medium that Atlas encountered during its formation and subsequent journey. These chemically inert elements become incorporated into ice crystals through physical trapping rather than chemical bonding, creating tiny inclusions that can be released when the ice sublimates under solar heating. The noble gas inventory provides information about the radiation environment and plasma conditions present in Atlas's birth stellar system. Radioactive isotopes created by cosmic ray bombardment during Atlas's interstellar journey provide natural clocks that can potentially constrain the duration of the comet's voyage between stellar systems. These isotopes decay with known half-lives, creating daughter products that accumulate over time and can be detected through careful spectroscopic analysis. The radioactive inventory represents one of the few direct methods for determining how long Atlas has been traveling through space since its ejection from its parent system. Crystalline versus amorphous ice structures within Atlas's nucleus reflect the thermal history experienced by different regions of the comet during its formation and evolution. Crystalline ice forms under relatively warm conditions or through annealing processes that allow water molecules to arrange themselves in ordered lattices, while amorphous ice preserves the disordered structure created by rapid cooling or radiation damage. The relative proportions of these phases provide insights into the temperature variations Atlas experienced over geological timescales. Organic refractory materials, complex carbon-bearing compounds that resist sublimation at typical cometary temperatures, concentrate in the outer layers of Atlas's nucleus as more volatile components escape during periods of solar heating. These materials gradually build up a lag deposit that insulates the underlying ice and regulates the rate of continued outgassing. The composition of this refractory residue reflects the cumulative effects of thermal processing and radiation damage that have modified Atlas's surface chemistry over millions of years. The chemical gradients between Atlas's surface and interior document the history of thermal and radiation processing that has affected different regions of the nucleus to varying degrees. The outermost layers show evidence of extensive alteration by cosmic rays and solar heating, while the protected interior preserves more pristine compositions that may closely resemble the original materials from which the comet formed. These gradients create a stratified structure that records the environmental conditions Atlas has experienced throughout its existence. Isotopic anomalies in elements heavier than hydrogen provide the most direct evidence for Atlas's extrasolar origin. As these signatures reflect the specific nuclear processes that operated in the comet's parent star and the surrounding interstellar medium, slight variations in the ratios of carbon, nitrogen, and oxygen isotopes may distinguish Atlas's composition from that of solar system objects, though detecting these subtle differences requires the most sensitive analytical techniques available to modern spectroscopy. The preservation of chemical complexity within Atlas's nucleus demonstrates the remarkable stability of molecular structures under the extreme conditions of interstellar space. Despite exposure to cosmic radiation, micrometeorite bombardment, and the near-perfect vacuum between stars, the comet has maintained its elaborate chemical inventory for millions of years. This preservation suggests that interstellar objects serve as effective vehicles for transporting complex organic molecules between stellar systems, potentially contributing to the chemical evolution of planetary systems throughout the galaxy. The temporal mysteries locked within Atlas's ancient nucleus stretch back to an epoch when our own solar system existed only as a cold, dark cloud of gas and dust drifting through the galactic disk. Radiometric dating techniques applied to meteorites suggest that solid materials began condensing in stellar nebulae approximately 4.5 billion years ago. But Atlas may preserve even older components that formed during earlier generations of stellar evolution. The comet carries within its frozen matrix a record of cosmic chemistry that predates the formation of Earth, the Moon, and every planet in our solar system. Isotopic analysis reveals signatures of nuclear processes that operated in massive stars during their final evolutionary phases, when temperatures and pressures in stellar cores reached levels sufficient to synthesize elements heavier than iron through rapid neutron capture reactions. These are process elements, created during supernova explosions that occurred before our sun's birth, became incorporated into the molecular cloud from which Atlas's parent stellar system eventually condensed. The comet's nucleus contains atoms that were literally forged in the nuclear furnaces of dying stars. The crystalline structure of ice within Atlas's interior preserves information about the temperature history experienced by different regions of the nucleus over geological timescales. Laboratory studies of ice crystallization kinetics suggest that the ordered phases detected in the comet's spectrum require either formation at relatively elevated temperatures or subsequent annealing through gradual warming over millions of years. The presence of crystalline ice provides clues about thermal processes that operated during Atlas's residence in its parent stellar system or during particularly intense periods of cosmic ray bombardment. Cosmic ray exposure ages, calculated from the abundance of spallation products within Atlas's nucleus, suggest that the outer layers of the comet have been exposed to high-energy particles for periods measured in tens of millions of years. These nuclear reactions create distinctive isotopic signatures that accumulate at predictable rates, providing natural chronometers that record the duration of exposure to galactic cosmic radiation. The measured exposure ages may reflect either the time since Atlas's ejection from its parent system or periods when the nucleus surface was uncovered by the protective dust mantle. The comet's dynamical age, the time required for its orbit to evolve from its point of origin to its current trajectory, depends critically on assumptions about the density and structure of interstellar space along its path. Computer simulations suggest that objects traveling at Atlas's velocity require several million years to cross the typical distances between stellar systems. But this estimate becomes highly uncertain when gravitational perturbations from passing stars and molecular clouds are considered. The true duration of Atlas's journey may exceed current estimates by factors of several. Trapped noble gases within the ice matrix provide additional chronological constraints through their relative abundances and isotopic compositions. These chemically inert elements become physically incorporated into crystalline structures during ice formation, creating microscopic time capsules that preserve samples of the stellar wind and interstellar medium present during Atlas's early history. The noble gas inventory may retain information about solar activity cycles and galactic environment conditions that existed billions of years ago. The thickness of the radiation-processed surface layer provides another indicator of Atlas's age and exposure history. Cosmic rays gradually modify the chemical composition of the outermost regions through nuclear reactions that break down complex molecules and create new isotopic species. Laboratory experiments with ice analogs suggest that the altered layer observed on Atlas's surface would require millions of years to develop under typical interstellar radiation conditions, providing independent confirmation of the comet's extended journey through space. Organic molecule complexity within Atlas's nucleus reflects the cumulative effects of radiation chemistry operating over astronomical timescales. Simple compounds like methane and carbon monoxide can be converted into more elaborate structures through bombardment by high-energy particles, creating molecular species that would be unstable under most terrestrial conditions. The inventory of organic compounds provides insights into the chemical evolution that occurs during extended exposure to cosmic radiation in cold, low-density environments. The comet's orbital characteristics encode information about the gravitational environment present during its ejection from its parent stellar system. Computer models of planetary system dynamics suggest that most interstellar objects are expelled during the early phases of stellar evolution, when massive planets migrate inward through gravitational interactions with protoplanetary disk material. Atlas's high ejection velocity implies that it experienced a close encounter with a massive object, possibly a gas giant planet or low-mass stellar companion. Metamorphic effects within Atlas's interior may preserve evidence of heating events that occurred during the comet's residence in its original stellar system. Thermal processing can alter the structure and composition of ice and organic materials in ways that remain detectable billions of years later, providing insights into the thermal evolution of the parent system's outer regions. The absence of significant metamorphic alteration suggests that Atlas originated from the cold, outer regions of its birth system, where temperatures remained too low for extensive chemical modification. The preservation of volatile compounds like carbon monoxide and methane places constraints on the maximum temperatures experienced by Atlas's nucleus during its interstellar journey. These substances would sublimate rapidly if exposed to significant heating, implying that the comet has remained consistently cold throughout its voyage between stellar systems. The survival of such volatile materials suggests that Atlas has avoided close encounters with hot stars or passages through dense molecular clouds, where elevated temperatures might cause chemical alteration. Magnetic field signatures trapped within dust grains in Atlas's nucleus may preserve records of the magnetic environment present in the comet's birth stellar system. Microscopic iron particles can retain magnetic orientations that reflect the direction and strength of magnetic fields present during their formation, creating natural magnetic tape recordings of ancient field configurations. These paleomagnetic signatures provide insights into stellar magnetic activity and the structure of magnetic fields in protoplanetary disks. The comet's internal structure, inferred from its rotational dynamics and outgassing patterns, suggests a formation process that involved gradual accretion of materials in a low-velocity environment. This gentle assembly preserved the layered structure and chemical heterogeneity that characterize many solar system comets, implying that similar physical processes operated during planetary system formation around Atlas's parent star. The nucleus architecture provides insights into the accretion mechanisms that operated billions of years ago in distant stellar nurseries, Seasonal variations in outgassing activity as Atlas approaches and recedes from the Sun reveal information about the thermal properties and internal structure of the nucleus. The response time to changing solar heating depends on the thermal conductivity and heat capacity of the comet's materials, properties that are influenced by porosity, composition, and the degree of sintering that has occurred over geological timescales. These thermal characteristics preserve information about processes that operated during Atlas's formation and subsequent evolution. The discovery of Atlas and other interstellar objects suggests that the galaxy contains a vast population of such wanderers, each carrying samples of materials from different stellar systems and epochs of galactic evolution. Statistical studies of interstellar object encounter rates imply that the spaces between stars are populated by trillions of these cosmic refugees, creating a galactic recycling system that redistributes materials processed in stellar cores throughout the Milky Way's disk. Atlas represents just one member of this vast population, a single data point in the grand experiment of galactic chemical evolution. The temporal perspective provided by Atlas's ancient nucleus challenges human intuitions about the permanence of celestial objects and the stability of planetary systems. The comet's existence demonstrates that even gravitationally bound stellar systems eventually disintegrate, ejecting their constituent materials into the galactic medium where they can be incorporated into new generations of stars and planets. Atlas carries within its frozen structure the memory of stellar death and rebirth, connecting our solar system to the broader cycles of cosmic evolution that operate over timescales far exceeding human civilization. As human instruments peer into the depths of space to study Atlas, the ancient visitor becomes an unexpected mirror that reflects back our own species' remarkable transformation from earthbound observers to cosmic archaeologists capable of analyzing materials that formed around distant stars. The very act of detection and characterization reveals as much about humanity's technological evolution as it does about the comet's composition and origin. Through studying this interstellar wanderer, we examine not only cosmic chemistry, but the extraordinary capabilities our species has developed to decode messages written in starlight. The telescopes trained on Atlas represent the culmination of 4 centuries of optical innovation, beginning with Galileo's crude refracting instruments and evolving into adaptive optic systems that correct for atmospheric turbulence in real time. Each photon collected from the comet carries information that would have been completely inaccessible to earlier generations of astronomers, demonstrating how technological progress expands the boundaries of human knowledge in ways that earlier scientists could never have imagined. The visitor becomes a test case for capabilities that were purely theoretical just decades ago. Spectroscopic analysis of Atlas's composition employs quantum mechanical principles that were unknown to the astronomers who first catalogued comets in our own solar system. The identification of specific molecules through their absorption and emission signatures requires detailed understanding of atomic structure and molecular dynamics that emerged only during the 20th century. The comet serves as a natural laboratory for testing theoretical predictions about how matter behaves under the extreme conditions of interstellar space. Computer simulations that model Atlas's trajectory through the galaxy rely on gravitational theories developed by Newton and Einstein, combined with numerical methods that were impossible to implement before the development of electronic computers. The precision of these orbital calculations demonstrates humanity's growing mastery of celestial mechanics, allowing astronomers to trace the visitor's path backward through time and predict its future motion with extraordinary accuracy. The comet becomes a validation of mathematical models that describe gravitational interactions throughout the universe. The international coordination required to track Atlas across multiple observatories reflects the global nature of modern astronomy, where scientific discoveries emerge from collaborative efforts that transcend national boundaries and political differences. The sharing of observational data and the coordination of telescope schedules demonstrate how the study of cosmic phenomena can unite human efforts in pursuit of knowledge that belongs to all humanity. The visitor catalyzes cooperation on scales that mirror the cosmic processes being investigated. Amateur astronomers contributing observations of Atlas through citizen science networks represent the democratization of astronomical research, where individuals with modest equipment can make meaningful contributions to professional investigations. This participation transforms astronomy from an exclusively academic pursuit into a collaborative endeavor that engages people from diverse backgrounds and locations. The comet becomes a focal point for public engagement with science, inspiring interest in cosmic phenomena among audiences far beyond the professional astronomical community. The detection algorithms that automatically identify moving objects like Atlas in survey images employ machine learning techniques that mimic aspects of human pattern recognition while operating at speeds and scales impossible for biological systems. These computational tools process millions of stellar images each night, distinguishing genuine moving objects from instrumental artifacts and cosmic ray hits with reliability that exceeds human capabilities. The visitor demonstrates how artificial intelligence enhances human ability to explore and understand the cosmos. Real-time data processing systems that generate updated orbital predictions for Atlas within hours of new observations exemplify the integration of observational astronomy with information technology. The rapid analysis and dissemination of results allows astronomers worldwide to coordinate follow-up observations and respond quickly to unexpected changes in the comet's behavior. The visitor benefits from computational infrastructure that transforms raw observational data into scientific knowledge at unprecedented speeds. The precision required to measure Atlas's position and velocity pushes astrometric techniques to their fundamental limits, where quantum uncertainty and general relativistic effects become measurable influences on the results. These observations test the accuracy of reference star catalogs and the stability of coordinate systems used to map stellar positions, revealing systematic errors that must be corrected to achieve the precision required for interstellar object studies. The comet serves as a calibration source for the most demanding applications of positional astronomy. Space-based telescopes observing Atlas operate in environments that eliminate atmospheric disturbances while introducing new challenges related to thermal stability, radiation damage, and limited operational lifetimes. The engineering solutions required to maintain precise pointing and stable temperatures in the hostile environment of space represent remarkable achievements in technological sophistication. The visitor benefits from humanity's growing capability to construct and operate complex instruments beyond Earth's protective atmosphere. The interpretation of Atlas's spectroscopic data requires laboratory studies of ice and organic compounds under conditions that simulate the extreme cold and vacuum of interstellar space. These terrestrial experiments employ techniques borrowed from material science, physical chemistry, and condensed matter physics to understand how molecular species behave under cosmic conditions. The comet motivates interdisciplinary research that connects astronomy with fundamental studies of matter and energy. Public outreach efforts inspired by Atlas's discovery demonstrate the power of cosmic phenomena to capture popular imagination and inspire interest in scientific careers. Educational programs that explain the comet's significance help communicate the methods and results of modern astronomy to audiences that will fund and conduct future research. The visitor becomes an ambassador for scientific literacy, illustrating the connections between technological capability and our understanding of the universe. The philosophical implications of studying objects like Atlas challenge anthropocentric perspectives on humanity's place in the cosmos by demonstrating the interconnectedness of stellar systems throughout the galaxy. The comet carries materials that were processed in stellar cores billions of years ago, connecting our solar system to cosmic evolution cycles that operate on timescales far exceeding human civilization. The visitor reminds us that we participate in processes that extend far beyond our planet, our star, and our local galactic neighborhood. The economic infrastructure required to detect and study Atlas reflects society's investment in basic research that may not yield immediate practical applications, but expands fundamental knowledge about natural processes. The telescopes, computers, and human expertise dedicated to tracking interstellar objects represent resources allocated to satisfy human curiosity about cosmic phenomena. The visitor demonstrates how scientific exploration creates value through the generation of knowledge and the development of technological capabilities with unforeseen applications. The preservation of observational data from Atlas in digital archives ensures that future generations of astronomers will have access to measurements that cannot be repeated once the comet departs our solar system. These databases become permanent records of a unique cosmic event, available for analysis using techniques that have not yet been developed. The visitor contributes to humanity's growing library of astronomical knowledge, expanding the empirical foundation for theoretical studies of galactic evolution and interstellar chemistry. The study of Atlas exemplifies how modern astronomy transforms human beings into time travelers capable of examining materials and processes that operated billions of years ago in regions of space unimaginably distant from Earth. Through the analysis of ancient starlight and cosmic chemistry, we extend our senses across the galaxy and back through geological epochs. The visitor serves as a messenger from the deep past, carrying information about cosmic conditions that existed before our planet. Our star and our galaxy had achieved their current configurations. The collaborative nature of Atlas research demonstrates how the pursuit of cosmic knowledge creates communities of scientists who share data, techniques, and insights across institutional and national boundaries. These collaborative networks represent emerging forms of human organization adapted to the global scale and long timescales characteristic of astronomical research. The visitor catalyzes new types of scientific cooperation that may serve as models for addressing other challenges that transcend local interests and short-term perspectives. The invisible architecture of magnetic fields threading through the space around Atlas creates a complex electromagnetic environment that shapes the behavior of charged particles in ways that remain largely hidden from direct observation. As the solar wind, that continuous stream of protons and electrons flowing outward from our star, encounters the comet's expanding coma, it creates disturbances in the local magnetic field configuration that can be detected by sensitive magnetometers aboard spacecraft scattered throughout the inner solar system. These interactions transform Atlas into a temporary source of electromagnetic phenomena that add another layer of complexity to its already rich observational signature. Solar wind particles approaching Atlas carry with them the twisted magnetic field lines that originate in the sun's corona and spiral outward through the solar system at velocities approaching 400 kilometers per second. When these magnetized plasma flows encounter the neutral gas expanding from the comet's nucleus, charge exchange reactions create new populations of energetic ions that respond to magnetic forces in ways that differ fundamentally from the behavior of uncharged molecules. The region around Atlas becomes a natural laboratory for studying plasma physics processes that operate throughout the cosmos. The process of ionization transforms ordinary water vapor and carbon monoxide molecules into electrically charged species that couple strongly to magnetic field lines embedded in the solar wind. Once ionized, these molecules no longer follow ballistic trajectories determined solely by gravity and gas pressure, but instead execute complex helical motions as they spiral around magnetic field lines while simultaneously drifting across field gradients. The comet's coma develops a dual personality, with neutral molecules expanding freely into space, while ionized components become trapped and accelerated by electromagnetic forces. Magnetic reconnection events occurring in the plasma environment surrounding Atlas release stored magnetic energy in explosive bursts that can accelerate particles to velocities far exceeding the typical thermal speeds present in the comet's coma. These reconnection episodes occur when magnetic field lines with opposite orientations approach each other closely enough to break and reconnect in new configurations, converting magnetic energy into kinetic energy of charged particles. The phenomenon creates temporary enhancements in radio emissions and X-ray production that can be detected by sensitive instruments throughout the inner solar system. The magnetic draping effect causes solar wind field lines to bend around regions where Atlas's neutral coma creates obstacles to the free flow of magnetized plasma. This deformation of the magnetic field topology creates induced currents that flow within the ionized portion of the comet's atmosphere, generating secondary magnetic fields that partially shield the nucleus from direct bombardment by high-energy solar wind particles. The interaction resembles the way water flows around a stone in a stream, but with magnetic field lines replacing fluid streamlines. Plasma waves generated by instabilities in the interaction region between Atlas's coma and the solar wind propagate throughout the local space environment at frequencies ranging from a few hertz to several kilohertz. These electromagnetic oscillations carry energy and momentum away from the comet while simultaneously heating the local plasma through wave-particle interactions that operate through resonant processes. Radio telescopes can detect some of these emissions directly, while others must be inferred from their effects on the propagation of signals from distant astronomical sources. The magnetic tail of Atlas extends for distances measured in astronomical units in the direction opposite the Sun, created by the stretching and draping of interplanetary magnetic field lines around the ionized component of the comet's coma. This invisible appendage contains twisted flux ropes and current sheets where magnetic energy becomes concentrated, occasionally releasing stored energy through magnetic reconnection events that accelerate particles to high velocities. The tail structure evolves continuously as the comet moves through regions of the solar wind with different magnetic field orientations and plasma densities. Pickup ions created when solar wind particles collide with neutral molecules in Atlas's coma acquire the bulk velocity of the solar wind while retaining some memory of their initial thermal motion around the comet. These newly created charged particles follow cycloid trajectories that carry them far from their point of origin, creating extended ion populations that can be detected by plasma instruments on spacecraft located millions of kilometers from the comet itself. The pickup process efficiently converts neutral gas into ionized plasma, fundamentally altering the electromagnetic properties of the space environment. The interaction between Atlas's magnetic environment and the interplanetary magnetic field creates boundary layers where plasma properties change rapidly over distances of only a few hundred kilometers. These transition regions contain steep gradients in magnetic field strength, plasma density, and particle energy that drive various types of plasma instabilities. The boundaries become sites of enhanced turbulence, where energy cascades from large-scale magnetic structures to small-scale fluctuations that ultimately heat the local plasma through dissipative processes. Magnetic mirroring effects trap some charged particles in regions where the magnetic field strength increases, creating local populations of energetic ions and electrons that bounce back and forth between magnetic mirror points. These trapped particles contribute to the formation of radiation belts around Atlas, though the comet's weak magnetic field and extensive neutral atmosphere prevent the development of stable trapping regions comparable to those found around magnetized planets. The mirror effects create anisotropic particle distributions that influence the propagation of plasma waves through the comet's magnetosphere. The electrical conductivity of Atlas's ionized coma allows current systems to develop, that couple the comet electromagnetically to the surrounding solar wind. These currents flow in closed loops that thread through the plasma environment, creating magnetic dipole moments that interact with the interplanetary magnetic field. The current systems dissipate energy through Joule heating, warming the local plasma while simultaneously creating observable signatures in the form of enhanced radio emissions and modifications to the magnetic field configuration. Magnetic field measurements made by spacecraft passing through Atlas's extended magnetosphere reveal the three-dimensional structure of field line draping and the locations where magnetic reconnection occurs most frequently. These in-situ observations provide ground truth for theoretical models of comet-solar wind interactions, while simultaneously testing our understanding of fundamental plasma physics processes. The measurements often reveal unexpected complexity in the magnetic field topology that challenges simplified theoretical descriptions of the interaction process. The seasonal variation in Atlas's outgassing rate as the comet approaches and recedes from the Sun creates corresponding changes in the strength and extent of magnetic field disturbances in the surrounding space environment. Higher gas production rates generate larger ionized comas that interact more strongly with the solar wind, creating more extensive magnetic perturbations that can be detected at greater distances from the nucleus. These temporal variations provide insights into the coupling between neutral gas dynamics and electromagnetic phenomena. Synchrotron radiation produced by high-energy electrons spiraling in Atlas's magnetic environment contributes weak but detectable signals across the electromagnetic spectrum from radio waves to X-rays. The intensity and polarization properties of this radiation encode information about magnetic field strength and the energy distribution of accelerated particles in the comet's plasma environment. Ground-based radio telescopes can detect the synchrotron signatures during periods of enhanced magnetic activity, providing remote diagnostics of particle acceleration processes operating in the vicinity of the nucleus. The magnetic memory embedded in dust grains expelled from Atlas's nucleus preserves records of magnetic field conditions present during the comet's formation and subsequent evolution. Ion-bearing minerals within these particles can retain magnetic orientations that reflect ancient field configurations, creating natural magnetic tape recordings that survive the journey through interstellar space. Analysis of these paleomagnetic signatures provides insights into magnetic field strengths and orientations that existed in the comet's parent stellar system billions of years ago. Alphen waves, low-frequency magnetic oscillations that propagate along field lines at velocities determined by the local plasma density and magnetic field strength, transport energy and momentum throughout Atlas's extended magnetosphere. These waves can travel vast distances without significant attenuation, carrying information about conditions near the nucleus to regions far downstream in the magnetic tail. The wave propagation creates a dynamic coupling between different regions of the comet's plasma environment. The magnetic field topology around Atlas influences the trajectories of cosmic ray particles approaching from interstellar space, creating shadowing effects that reduce the bombardment rate of the nucleus during periods when the comet's magnetic environment provides effective shielding. This protection may influence the rate of radiation-induced chemistry occurring in the comet's surface layers, potentially preserving organic compounds that would otherwise be destroyed by high-energy particle impacts. The magnetic shielding effect varies with solar wind conditions and the orientation of the interplanetary magnetic field. Magnetic substorms, explosive releases of stored magnetic energy analogous to auroral substorms in planetary magnetospheres, occasionally occur in Atlas's plasma environment when the rate of magnetic flux loading exceeds the capacity for steady-state dissipation. These events accelerate particles to high energies while simultaneously restructuring the magnetic field configuration in ways that can be detected by remote sensing techniques. The substorms create temporary enhancements in radio emissions and modifications to the plasma wave environment. The magnetic signatures associated with Atlas provide a new tool for studying the internal structure and composition of interstellar objects through their electromagnetic properties. Different materials exhibit varying degrees of magnetic susceptibility and electrical conductivity, creating distinctive signatures when they interact with the solar wind's magnetic field. These electromagnetic diagnostics complement traditional optical and infrared observations by probing physical properties that cannot be determined through spectroscopic techniques alone. The discovery that ATLAS generates detectable magnetic disturbances demonstrates the universal nature of electromagnetic phenomena in space, showing how even modest concentrations of ionized gas can create complex magnetic environments. The comet's magnetic interactions provide insights into similar processes that operate around other small bodies throughout the solar system and around objects in distant stellar systems. The electromagnetic signature of ATLAS adds another dimension to our understanding of how matter and energy interact in the cosmic plasma that fills most of the observable universe. The stellar cartography that traces ATLAS's origin reaches back through galactic time to regions of space where massive stars once lived, died, and scattered their nuclear ashes into the interstellar medium that would eventually condense into new planetary systems. Computer simulations that model the motion of stars through the Milky Way's gravitational field suggest that ATLAS began its journey from the general direction of the constellation Lynx. But this represents only the most recent segment of a trajectory that may have been shaped by gravitational encounters spanning millions of years and thousands of light-years of galactic real estate. The kinematic analysis that reconstructs ATLAS's galactic orbit relies on precise measurements of the comet's velocity relative to the local standard of rest, that theoretical reference frame defined by the average motion of stars in our galactic neighborhood. These calculations reveal that ATLAS approaches our solar system with a velocity vector that differs significantly from the motion expected for objects gravitationally bound to nearby stellar systems, confirming its origin from regions of the galaxy where stellar formation processes operated under conditions distinct from those present in our local environment. Stellar formation regions identified through infrared surveys of molecular clouds provide potential birthplaces for objects like ATLAS, though the specific stellar nursery that created the comet remains lost in the statistical uncertainty that accumulates over millions of years of galactic evolution. The most likely candidates include massive star-forming complexes that existed several million years ago at distances of hundreds or thousands of light-years from our current galactic location, regions where gravitational interactions between forming planets could have ejected small bodies into interstellar trajectories. The chemical composition of ATLAS's nucleus carries isotopic signatures that reflect the nucleosynthesis processes that operated in its parent star during the various phases of stellar evolution. Elements heavier than iron require rapid neutron capture reactions that occur only during supernova explosions or neutron star mergers, implying that the materials in ATLAS were enriched by such events before being incorporated into the molecular cloud from which its parent stellar system condensed. The comet becomes a carrier of stellar death, transporting atoms forged in cosmic catastrophes across the galaxy. Galactic archaeology techniques that study the chemical evolution of stellar populations suggest that ATLAS formed during an epoch when the Milky Way's metallicity, the abundance of elements heavier than hydrogen and helium, was lower than current values. This lower metallicity environment would have influenced the chemistry of planetary formation processes, potentially creating compositions that differ subtly from those characteristic of more recently formed stellar systems. ATLAS represents a sample of cosmic chemistry from an earlier phase of galactic evolution. The proper motion of ATLAS through our solar system reflects not only the comet's individual trajectory, but also the differential rotation of the galaxy itself. As stars at different galactic radii orbit the central black hole with varying periods and velocities, this galactic shear gradually separates objects that originated in the same stellar formation region, dispersing them throughout the galactic disk over timescales measured in hundreds of millions of years. ATLAS, has been caught up in this cosmic mixing process, carrying materials processed in one part of the galaxy to distant regions where they can be incorporated into new generations of stars and planets. The local bubble, a cavity in the interstellar medium created by ancient supernova explosions that swept gas and dust away from our galactic neighborhood, may have influenced Atlas's trajectory during its journey toward our solar system. This roughly spherical region of hot, low-density plasma extends for hundreds of light-years around the Sun and contains shock fronts and magnetic field enhancements that can deflect charged particles and influence the motion of small objects moving through interstellar space. The bubble's complex structure creates a three-dimensional maze that may trap some interstellar visitors while allowing others to pass through relatively unimpeded. Spiral density waves that propagate through the Milky Way's disk create time-varying gravitational perturbations that can alter the trajectories of objects moving between stellar systems. These waves, which manifest as the spiral arm patterns visible in external galaxies, compress interstellar material and trigger star formation while simultaneously creating gravitational anomalies that can deflect small bodies from their original paths. Atlas may have encountered several such density waves during its million-year journey, each encounter slightly modifying its trajectory and potentially extending the duration of its voyage. The galactic tide, the differential gravitational force exerted by the Milky Way's mass distribution on objects at different distances from the galactic center, creates subtle accelerations that can accumulate over astronomical timescales to produce significant changes in orbital trajectories. These tidal forces are strongest near the galactic plane and in regions where the stellar density varies rapidly, such as the boundaries between spiral arms. Atlas's path through these regions would have been influenced by tidal accelerations that slowly modified its velocity and direction over millions of years. Stellar encounters with nearby stars during Atlas's interstellar journey could have altered the comet's trajectory through gravitational perturbations that remain difficult to reconstruct due to the chaotic nature of stellar dynamics in the galactic disk. Computer models suggest that Atlas likely passed within a few light-years of dozens of stellar systems during its voyage, each encounter producing small changes in velocity that accumulated over time to create the trajectory observed today. The stochastic nature of these interactions makes it impossible to trace the comet's path backward to its specific point of origin. The age-metallicity relation that characterizes stellar populations in the galactic disk provides constraints on the epoch when Atlas's parent stellar system formed. Based on the chemical composition preserved in the comet's nucleus, stars formed during different periods of galactic evolution exhibit characteristic abundance patterns that reflect the cumulative effects of nucleosynthesis in previous generations of stars. The isotopic ratios measured in Atlas's spectrum may eventually allow astronomers to determine when and where in the galaxy its parent system formed. Dark matter substructure within the Milky Way's halo creates gravitational anomalies that can influence the motion of objects traveling through the galactic potential well over very long timescales. These invisible concentrations of matter, predicted by cosmological simulations but not yet directly detected, may alter the trajectories of interstellar visitors in ways that current models cannot predict. Atlas's path through the galaxy may have been shaped by encounters with dark matter subhalos that remain completely invisible to electromagnetic observations. The galactic habitable zone, the annular region around the galactic center where conditions may be suitable for the development of complex life, includes the location where Atlas likely originated, suggesting that its parent stellar system may have been capable of supporting planetary environments conducive to biological evolution. This possibility raises intriguing questions about whether objects like Atlas could transport organic compounds or even microscopic life forms between stellar systems, contributing to the potential spread of biology throughout the galaxy. Stellar kinematic studies that track the motion of individual stars through the galaxy reveal populations with different velocity dispersions and metallicities that reflect distinct formation epochs and galactic environments. Atlas's velocity, relative to nearby stars, places it within the kinematic signature expected for objects that originated from the galactic thin disk, the component of stellar populations that formed most recently and contains the highest concentrations of heavy elements. This kinematic association provides additional evidence for the comet's origin from a relatively young stellar system. The interstellar medium through which Atlas traveled during its journey contains density variations, magnetic field structures, and shock fronts created by stellar winds and supernova explosions that occurred throughout the galaxy's recent history. These features create a complex three-dimensional environment that influences the motion of small objects through drag forces, electromagnetic interactions, and gravitational perturbations. The cumulative effects of passage through this structured medium may have significantly altered Atlas's trajectory from its original ejection velocity. Future astrometric surveys that measure the proper motions of millions of stars with unprecedented precision will eventually map the galactic velocity field in sufficient detail to trace the dynamical history of interstellar objects like Atlas with much greater accuracy. These observations may reveal the specific stellar moving groups or kinematic structures from which such visitors originated, providing direct connections between interstellar objects and their parent stellar populations. Atlas represents an early example of the cosmic archaeology that will become possible as astronomical survey capabilities continue to advance. The acceleration anomaly detected in Atlas's orbital motion manifests as tiny deviations from the purely gravitational trajectory predicted by classical celestial mechanics, revealing forces that operate beyond the familiar realm of Newton's inverse square law. These non-gravitational accelerations, measured through careful analysis of positional observations spanning months of telescope tracking, suggest that the comet experiences subtle pushes and pulls that cannot be explained by the combined gravitational influences of the Sun, planets, and other massive objects in the solar system. Outgassing from Atlas's nucleus provides the most likely explanation for these mysterious accelerations, as molecules sublimating from the surface carry momentum that was originally part of the comet's orbital motion. The rocket effect created by this mass loss generates forces that depend on the rate of gas production, the distribution of active regions across the nucleus surface, and the rotational state of the comet. Computer models that incorporate these physical processes can account for most of the observed deviations, though significant uncertainties remain in the detailed mechanics of how outgassing creates net forces on irregularly shaped rotating objects. The asymmetric distribution of active regions on Atlas's surface creates preferential directions for gas emission that result in net forces even when the total outgassing rate remains constant. These jet-like features, revealed through high-resolution imaging of the comet's coma, produce stronger emissions from some areas of the nucleus while leaving other regions relatively inactive. The pattern of activity depends on the thermal properties of different surface materials and the orientation of subsurface ice deposits relative to solar heating, creating complex force patterns that vary with the comet's rotation period and seasonal changes in solar illumination. Thermal lag effects introduce additional complexity into the relationship between solar heating and outgassing-induced accelerations, as the temperature of Atlas's surface responds slowly to changes in solar radiation intensity. The thermal inertia of the nucleus materials causes peak outgassing rates to occur several hours after local noon on the comet's surface, creating a systematic offset between the direction of maximum heating and the direction of strongest gas emission. This lag generates net forces that can either accelerate or decelerate the comet's orbital motion, depending on the specific geometry of active regions and rotation axis orientation. The composition of gases escaping from Atlas's nucleus influences the magnitude of non-gravitational forces through the molecular weights and sublimation energies of different species. Water vapor, carbon monoxide, and carbon dioxide each produce different thrust coefficients when they escape from the surface, as their distinct molecular masses and thermal velocities determine the momentum transfer efficiency. Compositional variations across the nucleus surface create spatial patterns in the force generation that depend on the local abundance of different volatile compounds. Radiation pressure from solar photons contributes an additional acceleration component that becomes significant for objects with low bulk densities and high surface-to-mass ratios. Atlas's nucleus, with its fluffy structure and dark surface coating, experiences radiation pressure forces that depend on the cross-sectional area presented to the Sun and the efficiency with which the surface absorbs and re-radiates electromagnetic energy. These forces always act in the radial direction away from the Sun, but can be enhanced or diminished by the comet's rotational motion and irregular shape. The Yarkovsky effect, thermal re-radiation from a rotating object heated by solar radiation, creates systematic forces that can gradually alter orbital trajectories over extended periods. For Atlas, this effect depends on the thermal conductivity of surface materials, the rotation period, and the distribution of thermal inertia across different regions of the nucleus. The direction and magnitude of Yarkovsky forces depend critically on whether the comet rotates prograde or retrograde relative to its orbital motion, creating accelerations that can either expand or contract the orbit over time. Dust particles expelled from Atlas's nucleus carry significant momentum that contributes to the overall non-gravitational acceleration experienced by the comet. The size distribution and velocity of ejected dust grains determine the efficiency of momentum transfer, with larger particles carrying more momentum per unit mass, but smaller particles achieving higher velocities relative to the nucleus. The net effect depends on the balance between these competing factors and the rate at which dust production varies with solar distance and rotational phase. Electromagnetic forces generated by the interaction between Atlas's ionized coma and the magnetic field embedded in the solar wind create additional acceleration components that vary with space weather conditions and the comet's position relative to the Sun. These forces, though typically much smaller than those produced by outgassing, can become significant during periods of enhanced solar activity when the solar wind carries stronger magnetic fields and higher particle densities. The electromagnetic accelerations depend on the degree of ionization within the coma and the electrical conductivity of the nucleus materials. Seasonal variations in Atlas's activity level create corresponding changes in the magnitude and direction of non-gravitational accelerations as the comet approaches and recedes from the Sun. The increase in outgassing rates near perihelion produces stronger forces that can significantly alter the comet's trajectory, while the decline in activity at greater solar distances reduces these perturbations to levels that may become difficult to detect observationally. These temporal variations provide insights into the physical processes that control gas production from the nucleus surface. The rotational dynamics of Atlas's nucleus influence the time-averaged direction of non-gravitational forces through the complex interplay between surface heating patterns, gas emission directions, and the comet's tumbling motion. Computer simulations that model the detailed thermal and gas dynamics reveal how forces that appear random over short timescales can produce systematic accelerations when averaged over multiple rotation periods. The net effect depends on the obliquity of the rotation axis, the distribution of active regions, and the thermal response time of surface materials. Laboratory experiments with analog materials under simulated space conditions help calibrate theoretical models of outgassing-induced forces by measuring the momentum transfer efficiency for different ice compositions and thermal environments. These studies reveal how factors like porosity, contamination by dust particles, and the presence of organic compounds influence the relationship between gas production rates and the resulting forces on the parent object. The experimental results provide essential input parameters for numerical models that attempt to predict non-gravitational accelerations from observable properties of cometary nuclei. The detection of non-gravitational accelerations in Atlas's motion demonstrates the remarkable precision achieved by modern astrometric techniques, which can measure positional changes smaller than the apparent size of a coin viewed from a distance of several kilometers. These measurements require careful correction for systematic errors in telescope pointing, atmospheric refraction effects, and the proper motions of reference stars used to define the coordinate system. The achievement represents a triumph of observational astronomy and data analysis techniques. Comparative studies of non-gravitational forces affecting other comets provide context for understanding the acceleration anomalies observed in Atlas's motion. Solar system comets exhibit a wide range of force magnitudes and directional patterns that reflect differences in composition, structure, and rotational properties. The systematic study of these effects has revealed general principles that govern how sublimating ice creates net forces on irregular rotating objects. Principles that can be applied to interpret the behavior of interstellar visitors, like Atlas. The implications of Atlas's acceleration anomaly extend beyond the immediate challenge of accurately predicting the comet's trajectory to fundamental questions about the physical processes that operate in interstellar objects. The forces affecting Atlas provide insights into the internal structure, composition, and thermal properties of materials that formed in distant stellar systems billions of years ago. These measurements represent some of the most direct physical information available about objects that originated beyond our solar system. Future observations of Atlas as it continues its journey away from the Sun will reveal how non-gravitational accelerations evolve as outgassing rates decline and the comet returns to the frigid conditions of interstellar space. The long-term monitoring of these effects may provide unique insights into the processes that allow volatile compounds to survive extended journeys through the galaxy while maintaining their ability to sublimate when exposed to stellar radiation. Atlas becomes a natural experiment in the physics of interstellar transport and the preservation of chemical complexity under extreme conditions. The transformation of Atlas from a physical object into digital immortality begins the moment its reflected light strikes the sensors of terrestrial telescopes, converting ancient photons into streams of electrons that flow through computational networks spanning the globe. Each image captured by survey telescopes contains millions of pixel values that encode the brightness and position of countless stellar objects, creating vast databases that preserve observational information with precision and permanence that far exceed the capabilities of human memory or written records. Digital archives storing Atlas observations employ redundant storage systems and error correction algorithms that ensure the long-term preservation of scientific data against the inevitable degradation of physical storage media. Multiple copies of each observation exist in geographically distributed data centers, protected by backup systems and migration protocols that transfer information to newer storage technologies as older systems become obsolete. The comet's passage through our solar system becomes encoded in magnetic domains and solid-state memory cells that may outlast the original object by millions of years. The metadata associated with each Atlas observation contains detailed information about the telescope, detector, atmospheric conditions, and data processing algorithms used to generate the measurements. This ancillary information proves essential for understanding the limitations and systematic errors that affect each observation, allowing future researchers to properly interpret results obtained with instruments that may become obsolete or forgotten. The metadata creates a digital archaeology that preserves not only the observations themselves, but also the technological context in which they were obtained. Machine-readable formats ensure that Atlas observations remain accessible to automated analysis programs as computational techniques continue to evolve. Standardized file formats and coordinate systems allow software tools developed decades apart to process the same observational data, creating a temporal bridge that connects past observations with future analytical capabilities. The standardization represents an investment in scientific continuity that extends the useful lifetime of astronomical observations far beyond their original purpose. Pixel-level calibration data accompanies each Atlas image, documenting the response characteristics of individual detector elements and the corrections applied to convert raw instrument readings into calibrated brightness measurements. This information allows future researchers to reprocess the original data using improved calibration techniques, potentially extracting scientific information that was not accessible when the observations were first obtained. The preservation of raw data ensures that technological advances can be applied retroactively to historical observations. Version control systems track changes made to Atlas data processing algorithms, creating audit trails that document how observational measurements evolved as analysis techniques improved. Each version of the processed data carries information about the specific software versions, calibration files, and processing parameters used to generate the results. This computational archaeology allows researchers to understand how measurement uncertainties and systematic errors have been addressed in different versions of the same dataset. Distributed computing networks process Atlas observations using algorithms that automatically detect moving objects, measure their positions and brightnesses, and generate preliminary orbital solutions. These computational pipelines operate continuously as new observations arrive, updating orbital predictions and identifying objects that merit follow-up observation. The automated systems create a feedback loop between observation and analysis that accelerates the pace of discovery while ensuring that interesting objects are not overlooked due to the volume of data being processed. Digital object identifiers assigned to Atlas observations create persistent links that remain valid even as data storage systems and institutional affiliations change over time. These identifiers function as permanent addresses in digital space, allowing researchers to cite specific observations in scientific publications with confidence that future readers will be able to access the reference data. The identifier system creates a stable foundation for scientific reproducibility in an era when data volumes exceed human capacity for manual organization. Data fusion techniques combine Atlas observations from multiple telescopes and wavelength ranges into comprehensive datasets that provide more complete information than any single instrument could obtain independently. These merged datasets account for differences in telescope characteristics, observing conditions, and calibration systems to create homogeneous measurements that can be analyzed as if they came from a single, idealized instrument. The fusion process preserves the individual contributions while creating synthetic observations with capabilities that exceed those of the original instruments. Quality assessment algorithms automatically evaluate each Atlas observation for potential systematic errors, instrumental artifacts, and atmospheric effects that might compromise its scientific value. These systems flag suspicious measurements and assign confidence levels based on objective criteria related to signal-to-noise ratios, consistency with theoretical expectations, and agreement with observations from other telescopes. The quality control creates a tiered system of data reliability that guides users toward the most trustworthy measurements. Cross-correlation databases link Atlas observations with measurements of the same object obtained by different telescopes and research groups, creating networks of related observations that can be analyzed collectively. These connections reveal systematic differences between instruments and observing techniques while providing multiple independent confirmations of important measurements. The cross-correlations transform isolated observations into components of larger investigative frameworks that enhance the statistical significance of scientific conclusions. Long-term preservation strategies for Atlas data include migration to new storage technologies, format conversions that maintain compatibility with evolving software systems, and the creation of multiple independent archives that reduce the risk of catastrophic data loss. These strategies recognize that the useful lifetime of astronomical observations often exceeds the operational lifetime of the institutions and technologies that created them. The preservation efforts represent investments in future scientific discoveries that may depend on historical observations of objects that can never be observed again. Data mining techniques applied to Atlas observations reveal patterns and correlations that were not apparent when the data were originally collected. Machine learning algorithms trained on large datasets can identify subtle features in the observational record that escaped detection during initial analysis, potentially leading to new insights about comet behavior and interstellar object characteristics. The digital nature of the observations makes them amenable to analysis techniques that did not exist when the data were first obtained. Open access policies ensure that Atlas observations remain available to researchers worldwide regardless of their institutional affiliations or financial resources. These policies recognize that scientific data represent public goods whose value increases when they are widely accessible to the global research community. The open access approach maximizes the scientific return on investment in astronomical facilities while promoting international collaboration and the democratization of scientific research. The digital representation of Atlas creates opportunities for virtual reality and augmented reality applications that allow users to experience the comet's journey through three-dimensional visualizations based on actual observational data. These immersive technologies transform abstract numerical measurements into intuitive spatial experiences that can enhance scientific understanding and public engagement with astronomical discoveries. The digital format serves as a foundation for educational tools that make complex scientific concepts accessible to diverse audiences. Computational reproducibility protocols document the exact software versions, input parameters, and computational environments used to analyze Atlas observations, ensuring that scientific results can be independently verified by other researchers. These protocols address the growing challenge of computational complexity in modern astronomy, where sophisticated algorithms and large datasets make it difficult to reproduce published results without detailed documentation of the analysis procedures. The reproducibility standards create a foundation for cumulative scientific progress. The transformation of Atlas into digital form represents a fundamental shift in the nature of astronomical objects, which become simultaneously physical entities moving through space and information structures encoded in computational systems. This duality allows the comet to exist simultaneously in its original cosmic context and in virtual environments where it can be manipulated, analyzed, and experienced in ways that would be impossible with the physical object alone. The digital immortality of Atlas ensures that future generations will have access to detailed records of this unique cosmic visitor long after it has faded beyond the reach of even the most powerful telescopes. The departure protocol begins imperceptibly as Atlas reaches the maximum extent of its inward journey and begins the gradual process of climbing back out of our solar system's gravitational well. The comet's velocity relative to the Sun increases steadily as it converts gravitational potential energy into kinetic energy. Following the same conservation laws that govern all motion in the cosmos, each day carries Atlas farther from the warmth and radiation that briefly awakened its ancient ices, returning the visitor to the cold silence it knew during its million-year journey between the stars. The brightening that marked Atlas's approach toward perihelion reverses itself as decreasing solar radiation reduces the rate of sublimation from the nucleus surface. The coma that once extended for thousands of kilometers around the solid core gradually contracts as fewer gas molecules escape into space, while the tail that briefly decorated the comet's wake fades until it becomes invisible to all but the most sensitive instruments. The visitor's transformation back into dormancy follows the same physical laws that governed its awakening. But in reverse temporal sequence, ground-based telescopes continue tracking Atlas's recession through increasingly sophisticated techniques designed to extract information from the weakening signals. Adaptive optics systems compensate for atmospheric turbulence with growing precision, while digital image processing algorithms stack multiple exposures to detect the comet's fading light against the cosmic background. The technological challenge of maintaining observations grows steadily as Atlas's apparent brightness decreases, according to the inverse square law that governs the intensity of reflected sunlight. The orbital mechanics of Atlas's departure follow hyperbolic trajectories calculated with the same mathematical precision that predicted its approach. Though small uncertainties in the non-gravitational forces created by outgassing continue to accumulate as the comet moves through poorly understood regions of parameter space. Computer models project the visitor's path through the outer solar system and beyond, accounting for gravitational perturbations from the giant planets that will provide the final modifications to its trajectory before it returns to interstellar space. Gravitational assists from Jupiter and Saturn alter Atlas's departure velocity by small but measurable amounts, adding or subtracting orbital energy depending on the specific geometry of each planetary encounter. These interactions represent the solar system's final gifts to the departing visitor, modifications to its galactic trajectory that will influence its path through the Milky Way for millions of years to come. The perturbations demonstrate how gravitational interactions create connections between objects separated by astronomical distances and geological timescales. The heliosphere boundary marks the transition region where Atlas will leave behind the solar wind's direct influence and return to the interstellar medium from which it emerged. This boundary, located at distances exceeding 100 astronomical units from the Sun, represents the edge of our star's electromagnetic domain and the beginning of truly interstellar space. The crossing will occur decades in the future, long after Atlas has faded beyond the detection limits of terrestrial telescopes. Radio telescopes maintain contact with Atlas longer than optical instruments due to their superior sensitivity and the comet's continued production of weak electromagnetic emissions. The hydroxyl radical signatures that allow detailed chemical analysis during the comet's active phase persist at reduced levels as residual outgassing continues from protected ice deposits beneath the surface dust layer. These radio observations provide the last direct measurements of Atlas's composition as it transitions back to dormancy. The visitor's rotation state evolves continuously as asymmetric outgassing creates torques that gradually alter the orientation and period of the nucleus's tumbling motion. Computer simulations suggest that these changes will continue for years after visible activity ceases, as thermal cycling and residual gas emission slowly modify the comet's angular momentum. The rotational evolution provides insights into the internal structure and mass distribution within objects that originated in distant stellar systems. Long-term monitoring programs establish observational cadences designed to track Atlas's recession until it becomes too faint for detection by current instrumentation. These programs coordinate observations among multiple telescopes to ensure continuous coverage despite equipment failures, weather interruptions, and competing demands for telescope time. The monitoring represents humanity's attempt to maintain contact with an interstellar messenger for as long as technologically possible. The apparent magnitude of Atlas decreases predictably as the square of its distance from both the Sun and Earth, following photometric laws that allow astronomers to estimate the detection limits for various telescope systems. The calculations reveal that ground-based telescopes will lose contact with the visitor within a few years of perihelion passage, while space-based instruments may maintain detection capability for somewhat longer periods. The fading follows inexorable mathematical relationships that cannot be overcome through improved observational techniques. Archival observations collected during Atlas's passage through the inner solar system become increasingly valuable as the comet recedes beyond the reach of active observation programs. These historical datasets preserve detailed records of the visitor's behavior during its brief period of activity, creating permanent libraries of information that can be analyzed using future computational techniques. The archives represent humanity's attempt to preserve knowledge about objects that may never return to our vicinity. Theoretical studies of Atlas's long-term orbital evolution employ gravitational models that account for stellar encounters, galactic tidal forces, and perturbations from massive molecular clouds that the comet will encounter during its future journey through the galaxy. These calculations suggest possible trajectories that could eventually bring the visitor back to our solar system, though the timescales involved exceed the age of complex life on Earth. The theoretical work extends human knowledge far beyond the limits of direct observation. The gradual cessation of Atlas's observable activity provides insights into the physical processes that control the transition between active and dormant states in cometary nuclei. The shutdown sequence reveals how different volatile species cease sublimating as temperatures drop and how the formation of surface crusts can protect underlying ice deposits from continued solar heating. These observations improve theoretical models of comet evolution and thermal physics. Comparative studies analyze Atlas's recession behavior relative to similar objects observed during previous decades, searching for common patterns that might reveal universal principles governing comet activity cycles. The comparisons help distinguish between effects that depend on specific compositional or structural properties and those that result from fundamental physical processes common to all sublimating objects. The systematic approach builds empirical foundations for theoretical understanding. The electromagnetic signature of Atlas's plasma environment gradually weakens as reduced outgassing diminishes the production of ionized species that create detectable radio emissions and magnetic field perturbations. Space weather monitoring systems track the fading of these signatures as the comet's influence on local plasma conditions becomes negligible compared to solar wind fluctuations. The electromagnetic fade-out provides the last measurable evidence of Atlas's presence in our solar system. Navigation databases updated throughout Atlas's passage gradually remove the comet's gravitational influence from spacecraft trajectory calculations as its mass becomes negligible compared to other perturbations affecting interplanetary missions. The removal marks the formal end of Atlas's membership in the solar system's dynamic community, returning it to the status of an external visitor whose presence no longer affects local orbital mechanics. The computational transition reflects the physical reality of departure. Future encounter predictions calculate the probability that Atlas will eventually interact with other stellar systems during its continued journey through the galaxy. These statistical studies suggest that the visitor will likely experience close approaches to numerous stars over the next few million years, with each encounter potentially altering its trajectory and chemical composition. The predictions connect Atlas to the broader population of interstellar objects that migrate between stellar systems. The legacy of Atlas's passage extends beyond the observational data and scientific insights to include technological developments, international collaborations, and educational programs inspired by its discovery. The visitor catalyzed improvements in detection algorithms, data processing techniques, and coordination protocols that will benefit future studies of interstellar objects. The technological and social impacts ensure that Atlas's influence on human capabilities will persist long after the object itself has faded from view. The vast wilderness of interstellar space that awaits Atlas stretches across distances so enormous that light itself requires years to traverse the gaps between neighboring stellar systems. As the comet continues its hyperbolic trajectory away from our Sun, it enters a realm of cosmic geography where temperatures approach absolute zero. Densities rival the best laboratory vacuums, and the nearest sources of warmth and light remain separated by distances that dwarf the entire solar system. This is the domain where Atlas will spend the overwhelming majority of its existence. Drifting through the galactic dark with only the faint glow of distant stars to mark its passage, the local interstellar cloud that surrounds our solar system extends for dozens of light years in all directions, containing enough diffuse hydrogen and helium to create a tenuous medium through which Atlas must travel. This cloud, heated and ionized by radiation from nearby hot stars, maintains temperatures of several thousand degrees despite its extraordinarily low density. The paradox of hot but insubstantial gas demonstrates the exotic physics that operates in environments where matter becomes so dispersed that conventional concepts of temperature and pressure lose their familiar meanings. Magnetic fields embedded in the interstellar medium create invisible highways and barriers that influence the motion of charged particles, while leaving neutral objects like Atlas largely unaffected. These fields, with strengths measured in microgauss, represent the weakest magnetic environments in the known universe, yet play crucial roles in the dynamics of galactic evolution. The field lines threading through space carry information about ancient stellar explosions and the rotation of the galaxy itself, creating a magnetic memory that preserves the history of cosmic events spanning millions of years. Cosmic ray particles, atomic nuclei accelerated to nearly the speed of light by supernova shock waves and other violent astrophysical processes, provide the primary source of high-energy radiation that Atlas will encounter during its galactic wandering. These particles carry energies that exceed those achievable in terrestrial accelerators, creating nuclear reactions when they strike the comet's surface that gradually alter its chemical composition over geological timescales. The cosmic ray bombardment represents a slow but relentless erosion process that will continue throughout Atlas's journey. The heliosphere boundary, located at distances exceeding 100 astronomical units from the Sun, marks the transition between solar-dominated and galactic environments. At this interface, the solar wind encounters the interstellar medium in a complex interaction region where shock waves, magnetic reconnection, and plasma instabilities create turbulent conditions unlike those found anywhere else in the solar system. Atlas will cross this boundary decades in the future, entering a realm where our star's influence becomes negligible compared to galactic forces. Stellar encounters during Atlas's galactic orbit will periodically alter its trajectory through gravitational perturbations that depend on the masses, velocities, and impact parameters of passing stars. Statistical calculations suggest that the comet will approach within a few light years of perhaps a dozen stellar systems during the next million years, with each encounter producing small changes in velocity that accumulate over time to create significant modifications in its galactic trajectory. These random gravitational nudges ensure that Atlas's future path cannot be predicted with certainty over very long timescales. Molecular clouds, vast concentrations of cold gas and dust where new stars are born, occasionally obstruct the paths of interstellar objects like Atlas, creating temporary environments where densities and temperatures differ dramatically from typical interstellar conditions. Passage through such clouds can subject visitors to enhanced radiation, magnetic fields, and gravitational perturbations that may significantly alter their trajectories and surface properties. The clouds represent islands of concentrated matter in the cosmic ocean, environments where the chemistry and physics of star formation create conditions that have not existed in our solar system for over 4 billion years. The galactic gravitational field provides the underlying framework that governs Atlas's motion on the largest scales, creating a smooth potential well centered on the supermassive black hole at the Milky Way's core. This field accelerates objects toward the galactic plane while simultaneously causing them to orbit the galactic center with periods measured in hundreds of millions of years. Atlas participates in this grand rotation, joining the community of stars, gas clouds, and dark matter that collectively define our galaxy's structure and evolution. Dark matter concentrations, invisible to electromagnetic observations, may influence Atlas's trajectory through gravitational interactions that remain largely theoretical due to the elusive nature of this mysterious substance. Current cosmological models suggest that dark matter outweighs ordinary matter by factors of 5 to 1, creating gravitational structures that shape the large-scale distribution of galaxies while remaining completely transparent to light. Atlas may encounter dark matter subhalos during its journey, experiencing gravitational accelerations from objects that cannot be detected through conventional astronomical techniques. The cosmic microwave background radiation that fills all of space provides a gentle but uniform heating source that maintains Atlas's surface temperature at approximately 3 degrees above absolute zero. This ancient light, released when the universe first became transparent to electromagnetic radiation, creates an isotropic bath of photons that represents the afterglow of cosmic creation. The background radiation ensures that Atlas will never reach true absolute zero, maintaining a minimum temperature that reflects the thermal history of the universe itself. Gravitational waves passing through the galaxy create minute distortions in space-time that affect all matter, including objects as small as Atlas's nucleus. These ripples in the fabric of reality, generated by colliding black holes and neutron stars throughout the cosmos, carry information about the most violent events in the universe while simultaneously providing subtle perturbations to the motion of every object they encounter. The waves represent a form of cosmic communication that operates through the geometry of space-time itself rather than electromagnetic radiation. Galactic chemical evolution continues around Atlas as successive generations of stars synthesize heavy elements and distribute them through supernova explosions and stellar winds. The comet witnesses this ongoing enrichment of the interstellar medium, though the timescales involved ensure that any changes occur too slowly to be detected during human lifetimes. Atlas becomes a passive observer of cosmic metallicity, increases that operate over periods longer than the age of complex life on Earth. The spiral density waves that create the Milky Way's distinctive arm structure will periodically compress the interstellar medium around Atlas, triggering episodes of enhanced star formation in its vicinity. These waves propagate through the galactic disk at velocities different from the orbital motion of individual stars, creating a pattern that rotates more slowly than the material it contains. Atlas will experience multiple passages through spiral arms during its galactic orbit, witnessing the birth of new stellar generations in regions where gravitational compression overcomes thermal pressure. Interactions with other interstellar objects during Atlas's journey remain statistically unlikely due to the vast volumes of space involved, but such encounters could produce significant changes in trajectory or even physical collision if they occur at relative velocities typical of galactic motion. The interstellar population likely contains millions of similar objects ejected from planetary systems throughout the galaxy's history, creating a sparse but extensive community of cosmic wanderers that may occasionally interact through gravitational or physical encounters. The magnetic field of the galaxy itself, generated by the differential rotation of ionized gas and sustained by dynamo processes operating in the galactic disk, creates large-scale structures that influence the propagation of cosmic rays and the dynamics of the interstellar medium. Atlas travels through this galactic magnetic environment, experiencing field strengths that vary with location and time as the comet moves through different regions of the Milky Way's magnetic architecture. The field provides an invisible backdrop that shapes the electromagnetic environment throughout the galaxy. Tidal forces from the galaxy's central black hole and the gravitational influence of satellite galaxies create systematic accelerations that affect objects throughout the Milky Way. Though these forces become negligible for small objects like Atlas, except over extremely long timescales, The tidal environment represents the influence of cosmic structures on scales far larger than individual stellar systems, connecting Atlas's motion to the dynamics of galaxy formation and evolution that operate over periods comparable to the age of the universe. Future stellar encounters may eventually capture Atlas into a new planetary system, where it could experience another brief period of activity before resuming its dormant state in a different stellar environment. The probability of such capture remains extremely low, but the possibility ensures that Atlas's story may include multiple chapters of awakening separated by eons of quiescent wandering. Such captures would provide opportunities for life forms around other stars to study materials that originated in yet other stellar systems, creating a network of scientific exchange that operates over galactic scales. The heat death of individual stars will gradually reduce the number of potential targets for future encounters as the galaxy's stellar population ages and stellar formation rates decline. Atlas may outlive most of the stars that currently illuminate the Milky Way, continuing its journey through an increasingly dark and cold galaxy where stellar encounters become ever more rare. The comet's longevity depends primarily on its resistance to cosmic ray erosion and occasional gravitational disruption, processes that operate on timescales far exceeding stellar lifetimes. The ultimate fate of Atlas remains tied to the cosmological evolution of the universe itself, as dark energy accelerates the expansion of space and gradually separates gravitationally bound structures like galaxies. Over periods measured in hundreds of billions of years, the Milky Way will become increasingly isolated from neighboring galaxies, while internal processes like stellar evolution and galactic mergers reshape the environment through which interstellar objects travel. Atlas's journey connects intimate scales of molecular chemistry to the grandest scales of cosmic evolution. The eternal wandering that defines Atlas's existence transforms the comet into a messenger that carries information about stellar nucleosynthesis, planetary formation, and galactic dynamics across spatial and temporal scales that dwarf human comprehension. Each atom within its nucleus preserves isotopic signatures of nuclear processes that operated in stellar cores billions of years ago, while its trajectory encodes information about gravitational interactions with objects whose very existence may be forgotten by the time Atlas encounters its next stellar system. The visitor becomes a moving library of cosmic history, a traveling archive of the galaxy's past that continues its journey through the expanding universe long after the civilizations that briefly observed its passage have faded into cosmic history. The mathematics fade now into something softer than equations, something quieter than the precise language of orbital mechanics and spectroscopic analysis. Atlas continues its journey outward, each second carrying it farther from the brief warmth it knew during its passage through our solar system. The comet's story becomes part of the larger silence that fills the spaces between stars, a silence so profound that it transforms absence into presence, emptiness into meaning. In the growing darkness beyond Neptune's realm, where sunlight becomes indistinguishable from starlight, Atlas resumes the patient rhythm that has characterized most of its existence. The nucleus surface cools toward the background temperature of space itself, while the last wisps of sublimating gas freeze back onto the solid core or escape forever into the cosmic vacuum. The visitor returns to the state of deep dormancy that preserved its ancient chemistry through millions of years of galactic wandering. The telescopes that tracked Atlas through its brief awakening gradually lose contact as the comet fades below their detection thresholds. One by one, the observational programs end their monitoring campaigns, filing final reports that add Atlas to the growing catalog of interstellar visitors that have graced our solar system with their presence. The data archives preserve digital memories of reflected sunlight that will outlast the physical object itself. Radio emissions from the dissipating coma provide the last faint signals that connect Atlas to human consciousness. weak whispers in the cosmic static that gradually merge with the background radiation that fills all of space. The electromagnetic signatures fade until they become indistinguishable from the ancient light that has traveled since the universe first became transparent to photons. The visitor's voice joins the cosmic chorus of radiation that carries information across astronomical distances and cosmological timescales. Time dilates into geological rhythms as Atlas returns to the realm where individual years become meaningless units compared to the millions of rotations required to traverse the distance between stellar systems. The comet settles into the deep time of galactic evolution, where continental drift represents rapid change and stellar formation cycles provide the basic unit of temporal measurement. Human civilization, if it endures, may rise and fall countless times before Atlas encounters another star. The boundary between our solar system and interstellar space approaches with mathematical inevitability, marked not by visible landmarks, but by gradual changes in the electromagnetic environment and the composition of the surrounding medium. Atlas will cross this threshold in the cosmic equivalent of a gentle exhalation, transitioning from visitor to wanderer, from temporary to eternal. The passage will occur without ceremony, noticed only by the instruments that continue monitoring the outer reaches of heliospheric influence. Gravity provides the only remaining connection between Atlas and our solar system, a force that weakens according to inverse square laws but never quite reaches zero. The mathematical relationship ensures that some infinitesimal influence will persist even when the comet reaches distances measured in light years, creating a bond too weak to measure but too fundamental to break entirely. The gravitational memory connects Atlas to our Sun across the vast emptiness of interstellar space. The stellar cartographers of future civilizations may someday detect Atlas during its passage through other planetary systems, identifying it as an ancient wanderer whose isotopic signatures encode memories of stellar nucleosynthesis that occurred before their sun was born. These hypothetical observers will study the same chemical clues that revealed Atlas's extrasolar origin to terrestrial astronomers, reading stories written in atomic nuclei by processes that operated in distant regions of the galaxy billions of years ago. Dreams of spacecraft missions to intercept Atlas before it departs our vicinity remain technological fantasies, limited by the vast distances and enormous velocities that characterize interstellar trajectories. The visitor recedes at speeds that challenge current propulsion capabilities, while following a path that leads inevitably toward the galactic wilderness where no human-made object has yet traveled. Atlas carries our scientific attention to regions of space that may remain beyond direct exploration for centuries or millennia. The comet becomes a meditation on permanence and change, embodying both the eternal wandering that characterizes matter in the universe and the brief moments of activity that mark encounters with stellar radiation. Its existence spans timescales that reduce human history to an instant while participating in cosmic processes that connect the smallest scales of atomic physics to the largest structures of galactic architecture. Atlas transforms scientific observation into cosmic poetry. In the end, the visitor simply continues, following gravitational trajectories and chemical processes that operate with the same reliability in the darkness between stars as they do in the familiar warmth of planetary systems. The universe reveals itself as fundamentally hospitable to wandering, a place where objects can maintain their integrity across astronomical distances and geological timescales. Atlas demonstrates that even the cosmic void contains pathways for matter to travel, carrying information and complexity from one stellar system to another through the patient operation of physical laws that remain constant throughout space and time. The ancient ice sleeps now in the growing cold, preserving within its crystalline structure the memory of molecular clouds and stellar formation regions that may no longer exist. Atlas carries this frozen library through the galactic night, a traveler whose journey connects the deep past to an unknowable future. The comet fades into silence and darkness, joining the vast population of objects that populate the spaces between stars and maintain the slow circulation of matter that operates throughout the cosmos. Nothing remains but starlight and mathematics, cosmic rays and gravitational fields, the gentle pressure of ancient photons, and the invisible influence of dark matter concentrations. Atlas continues its eternal orbit through the galaxy's spiral arms, a messenger whose meaning transcends its physical presence, a wanderer whose story becomes part of the larger narrative of cosmic evolution that connects every atom to every star. The universe sleeps and dreams and continues,